So what if I told you that you can actually train a large language model without any NVIDIA or AMD hardware? What if I also told you that you can do this all in an iGPU? So today we're actually going to now fine tune a large language model using our Intel Arc GPUs. First, where I'm going to show you how to fine tune them using the Arc B580s end to end. So that means from synthetic data generation to evaluation of the data set, and then training it, and then benchmarking the model. After that, what's even more interesting is instead of just training on the B580s, why not train on this thing here, right? This AI Copilot mini PC that has Linux on it. And this is the Lunar Lake platform with the Arc 140V. So once we get everything done on our B580s, we'll attempt to do the same thing on a mini PC and see how the performance is for fine tuning and whether or not something like this is actually viable. What I'm trying to prove today is that you can fine tune on an Intel based system. Not only that, but you can do it in a very economical way, right? Like a low cost solution. Instead of buying a DGX Spark, if you know that your model can fit in VRAM of a mini PC like this, you could definitely just get one, fine tune your model, and then deploy it to wherever you want it to deploy. So yeah, let's get started. Should be fun. This video is going to be longer. I'm going to take my time to explain as much as possible. There's going to be some coding. I just be patient with me. I might get stuck, but yeah, let's just do it. So first things first, all of this is going to be, again, noted down in a blog post that I've written. It's called Fine Tuning LLMs on Any Intel Arc GPU. It's a living document, so check back often for any updates. So this blog post will be useful in the future if you ever need to reference again how to start fine-tuning on an Intel Arc based GPU. And it goes through end-to-end in terms of taking a base model and then generating the data you need to then perform the fine-tuning on your Intel specific hardware. Today, just a preview, we're going to be using the Arc B580 system that we've built to fine-tune a Qwen 3 0.6B model. So it's only 600 million parameters, but it will prove the point. We're going to fine-tune it on fixing some JSON payload. Basically, if you've ever used JSON lint, JSON validator, you paste in some bad JSON, it gives you back fixed JSON, or at least no formatted JSON. And if the JSON is bad, it'll say that it's an invalid JSON, right? But those tools really only go up to that point, and if your content inside that JSON happens to be invalid, such as like having blank lines instead of new line escape characters, for example, that would totally break your JSON. But JSON validator wouldn't be able to catch and fix that. So we're going to train the AI model to do that for us. So we'll have not only something that can lint and validate and fix JSON, or fix JSON in terms of like structure and spacing, but also fix the content inside. And we'll be able to take its base performance from 54% to about 87% in the small training data set that we will have. Okay, so we'll be needing to download the Qwen 3 0.6B model, and then we'll reuse our GPT OSS 20B model to be the model that we'll use for generating data. We'll also use a TRL library to fine-tune the model. We'll write the training script necessary, and then we'll use a mix of VLLM and Llama CPP to test the fine-tuned model. The reason why we need Llama CPP here is because I do want to demonstrate CPU inferencing and see how fast that is on smaller models like this. This is because, one day the goal is to be able to deploy on these edge devices, right? These mini PCs, and have them sit and do work for us. So it's helpful to understand, like, maybe we want to be hosting like two models in the PC, one that is GPU heavy and one that is lighter on the GPU that can be inferenced on the CPU. So it just depends. So it's nice to know how fast we can go there. So we'll write the code for everything from scratch. And again, here's a preview of the systems that we'll be using. We'll be doing everything on the B580s first, and then we'll just quickly demonstrate training on the mini PC with the ARC 140V. Okay, this guide assumes that you have Linux installed already, and for myself, I'm already SSH'd into the XPU system, the machine that we built in the last video. And so I already have the repo cloned, but it has nothing right now. It just has the license file and then the text file that I create to just have some quick test cases that we can run. You'll also need to have the Intel client DGPU drivers installed in the oneAPI based toolkit. You should be able to know how to create a virtual environment with Torch XPU and the right version of PyTorch Triton XPU. If you don't know how to do that, refer to the last video on how we set up VLLM for our Intel Arc. And then Llama CPP. You'll just need to build the latest from main branch and be able to know how to convert your safe tensors to GGUF, and then just learn how to run Llama server. Plenty of guides on how to do that. I even have a few videos that quickly explain that. We will do the same thing here, but it will be very light on the instructions. We already have our environment or our repo already set up and cloned. We just need to set up a virtual environment and then download all the requirements, and we'll go from there. The first thing I'll do is, since this is an empty environment and we want to set up for it being a proper Git repository. Oh yeah, I should mention that all the code is already available. I'm just working off of a branch just to be able to say I'm coding it all from scratch, but I've already done everything here, and the repo has all the code checked in already, so you can always just like reference what you need in this case. Like, for example, like if you want to understand what prompt was used to generate the data, you can go into the data processing Python class or Python scripts and just look at what I did here. The Python here is very basic. I just try to code as basic as possible, nothing fancy, so it should be a readable code. Okay, now let's really go back. Okay, so we'll initialize our git ignore, so npx git ignore Python. So we'll create a git ignore with a bunch of Python related files that we want to ignore. So here's just a preview. After that, we'll want to create a virtual environment. So again, let's stick to Python 3.12 because we know that works, and we'll just create it within the directory of our Git repo. We'll source that. So let's activate our virtual environment. So now we know that our virtual environment is activated when we see this .venv here. So we're going to need to install a few requirements. So going back here to this guide, we'll need setup tools. We'll also need the proper versions of Torch, Torch Vision, and Torch Audio off from the XPU wheel. And then we'll need to also make sure we download PyTorch Triton XPU at version 3.5 0. We'll also need transformers and TRL, and then I should have put also the OpenAI and JSON lines library, which I'll do later, but we'll also need to install that too. And then our repo is also its own module, since we want to be able to import correctly from other files that we write. So then we'll also install ourselves too, as long as we have a setup.py created. After that, we're going to just freeze freeze our modules into requirements.txt, so we can just reproduce the entire setup all the time. So the first things first, we'll just pip install setup tools, and that allows us to use setup.py. So we'll just paste that in here. And then since we're in a virtual environment, it'll just download the dependencies to our current environment. And then we'll download Torch, and this will be the XPU version. We have to make sure we always provide that index URL, because that will tell us, or tell pip to get the dependencies from this location here, which contains XPU stuff. So we'll do that. Paste that in here, and then it should go. And it should take a few minutes. Okay, so Torch with XPU has finished installing. We'll go back now and then install the PyTorch Triton XPU dependency. So let's do that. It's just oops, that's my anti-gravity. So let's do that and just paste it in. Again, provide that index URL. It's very important, otherwise you're going to get the wrong thing. And then now let's install transformers TRL, and then we also have the OpenAI and JSON lines library. Transformers TRL, OpenAI, JSON lines. So we need the OpenAI library and JSON lines for data set processing, transformers and TRL just for like the model stuff. So let's just let that go. And then last, we're going to install our own module, but we need to create a setup .py file in order for us to be able to pip install our own module. Okay, so that looks good now. And I have the project already opened up in anti-gravity. And so this is where we're going to be working for the rest of the time here. And I already had the tmux session open in the terminal pane. From time to time, I'll just be resizing like this. Okay, so we need our setup.py. And I'm kind of lazy. I know this is bad, but I'm just going to copy and paste because I don't want to type all that unnecessary scaffolding code out. So I'll just copy and paste from the repo here. Just copy the raw version, and then I'll just paste it in to anti-gravity, so that just sets up our project correctly. And then let's create a source folder. Oops. Let's create that source folder. So now all our code is going to be living here. So now that we have a setup.py, in that same directory, we can just do pip install -e period, and then that means relative directory, like the current directory. And yeah, we're good to go here. So the next thing we want to do is, now that we have all our dependencies installed, we want to pip freeze, and we want to save that into requirements.txt. Now, to always have these sets of dependencies installed properly on another, let's say you want to work on this project on another Intel Arc based system, you want to have this be easy to install. So what I like to do is I usually get rid of this, and I'll just always install that manually, and then I'll provide the URL to grab the right torch the dependencies and the PyTorch Triton XPU dependencies. So basically this torch here this torch here, and PyTorch Triton XPU here. So that, remember when we had specified the pip install earlier, we provided that index URL. So we want to actually provide that in here too, so that it automatically knows where to look for. So extra index URLs, the argument that we want to provide. So that would be https download.pytorch.org/whl XPU. So that's what we need to do. Okay, at this point, I think it makes sense to commit. We can also just try installing the requirements again, just see if that works. I don't think it has to be a fresh environment, so it seems like it picked all that up just fine, so our requirements.txt isn't broken. So what we can do here now is just do a commit. I don't want to check in the quick test cases yet. In fact, let's just add it to our git ignore. So then we can just do git add dot. So quick test cases.txt. So now when we add to git ignore, we won't have this showing up as wanting to be added. We can just do git add dot now and look at the git status. We'll do git commit dependencies. So I'm not going to push yet, but now we're in a state where we have all our dependencies installed correctly. So it's time to move on. Okay, moving on. We need to understand the problem that exists for us, the problem that we're trying to solve. So I don't know about you, but I copy and paste JSON a lot. And when I copy and paste JSON, it tends to be very sloppy JSON. And sometimes that JSON isn't even valid. Sometimes I'm just like typing up a quick example to show a person what some payload looks like. And oftentimes I might miss quotes around a key, or I forget that I need escape sequences within the content. And then I go off and try to pass that payload into something downstream to consume that JSON, and it just fails. So usually my instinct is to go and use a tool like JSON-lint and try to prettify it so that I can debug what's actually going on. So I hit validate JSON here on this specific tool, and I do get like sort of debug information, right? Debug output on what's exactly wrong with my JSON. As you can see here, what's really broken is this B key. And let me just go back here. It's really easy to see. This B key is not quoted correctly, and then this great job, Bill, you've got it with two necessary escape characters to be able to represent that JSON properly. So for example, what we really wanted was this payload here. So these two are from the same like conceptual content, except that this is the correct JSON representation. So here we have the quotes around the B key, and we also have the necessary new lines to represent visually this content here. So if we copy and pasted that to JSON-lint, we'll find that it validates correctly. So this is what we want our AI model to do. We want it to not only take payload and format it correctly like this in terms of making it pretty, like indentation and things like that, but we also want it to automatically correct the JSON by adding like quotes around keys that don't have quotes, and adding the proper escape characters to make that content valid. And that is like a step up from JSON-lint, because JSON-lint and maybe JSON validator only actually validates and prettifies the JSON, and it only prettifies if that JSON is valid to begin with. So this will be a very useful tool, and we can actually train an LLM to do this competently. In fact, even if the LLM got most of it correct, at least it will be easier to debug because you'll have less errors, and you can actually throw the rest into JSON-lint to find the rest of the problems that might exist. It'll be less overwhelming. Okay, so yeah, So here's like another example. You notice how all like the keys here aren't even quoted, and then some content here isn't even quoted at all. You'll have messy lines here, and then values that can break because they also again don't have quotes. So all of this should be able to be fixed just like this, right? So that's the goal. Notice how even like arrays are now formatted like they're like prettified in this case. And yeah, like you might think that you need a really big smart model to do this, but actually not. In fact, today we're only going to be using that Qwen 3 0.6b, which is like a 600 million parameter model. So it's actually very small. It's about 1.2 gigabytes of space needed to store the model and also represent that in VRAM. So lightweight, should be very fast, and it's proof that like small language models are very useful for these types of tasks. If you have like a very focused task, and you know that like how to create a data set for it, so that you can teach the model that ability. Definitely, small language models are the way to go. Especially when latency really matters if you're deploying it to production at the edge. So the first thing we need to do is create that data set. So without a data set, we can't really teach the model anything because you need to show the model like what does a typical input look like, and then like what output do you want it to produce given this type of example. And when you give enough of it, the AI model will start to pattern match and understand, oh, okay, like, so whenever I see this type of input, you want me to generate an output that looks like these examples I've been trained on. And the better the more data you give it, the better it generalizes to that so that it kind of knows how to do it correctly. So the plan is that we're going to, instead of manually by hand creating a lot of these examples where we show bad JSON and then here's good JSON, we're going to create a script that will generate that data using another LLM that is smarter. So in this case, GPT OSS 20B, and we'll have GPT OSS 20B generate that data. And then we'll take that data and we'll split that data to a specific ratio of training data, evaluation data, and test data. And then we're going to evaluate the quality of that data. So we need to create another script to go through that data, first to dedupe any examples, and then actually check to see if the ground truth generated by GPT OSS 20B is actually valid JSON. Like, is it actually fixed JSON? And for that, we need to use an LLM as a judge to do that filtering. And more about that later. And then finally, like if we find that after that evaluation, we're only keeping about a subset of the data that we've generated, we'll just repeat the process in generating data and then evaluating that data set until we get enough examples to use for training. So our workflow is going to be something like this. Generate data. So generate X examples. In this case, it could be 1,000. Okay, and then we're going to evaluate quality. Where we only keep a subset. So keep, well, let's say keep high quality examples, HQ examples. And then we're going to repeat that until we get enough examples. Now that's a simple diagram, right? But when it comes to evaluating quality, this is where I kind of want to like zoom into a little bit. How do you evaluate quality, right? So quality. We want to just understand whether or not the generated, generated ground truth really is the fixed and valid form of the invalid JSON given. So how we can do that is, can we convert the string? So the string, which is basically the ground truth representing as JSON, to a JSON object. If we can convert that in code, that means it's valid, right? Like JSON.loads in Python. If we can do that, then of course that is valid JSON. And also our keys and values. So our keys and values, I guess correct, right? Or the same as the invalid. So we don't want the model to kind of like remove keys or modify key names. So for example, like one instance is like, suppose you have like white space, right? White space around here, and then have a key A here as like a key. Well, this is actually a valid key in JSON. You don't want a fixed version to just say key A because there was like a white space. That's not correct, right? You want this to be maintained. You want this white space to be maintained. So you're like checking for things like that. And that's like what a high quality example is. If we can actually convert the string of that ground truth that represents that JSON to a JSON object, that means it's valid JSON. And then if the keys and values are like still the same as the invalid, it's just that maybe like values needed correct escape sequences, that would be okay. Like that's like an exception. And all of this, like these criteria, right, all of these criteria will be written in a prompt. So it'll be in a prompt. Okay, so that's the evaluation part. So we need to do this so that we don't expose examples to the small model while we're training that actually are contradictory to what we want it to do, right? Like any sort of bad example will teach the model the wrong thing, and that results in decreased accuracy in this case. So yeah, that's the evaluation part. And the generation part is pretty easy. Again, we'll just use, in this case here, GPT OSS 20B with our VLLM instance to get the examples that we want using a prompt, and then a loop that will just constantly send chat completion messages to the VLLM server. But here, this one is trickier. We need to use a different LLM. Okay, and here for myself, I cheated here. I used the OpenAI API. I use GPT 5.2 to evaluate the data. And for this one, you could use any other thing as long as it's a different LLM. And try to get a LLM that is smarter than OSS 20B, because you want that LLM to be capable of understanding like what is good and what is bad for JSON, right? So it has to have some smarts in it, but you also want it to be a different LLM, because you don't want to use the same LLM that generated the data to evaluate the quality of the data, because that's just the same thing as like you correcting or grading your own test. That's not really a good thing. You want a different LLM to judge like the quality and the work of that other LLM, because that's like having your teacher or your study partner actually correct your test that you've performed, right? The test that you did. I'm trying to use school analogies, so that should make sense, right? Like, so I cheated a little and used GPT 5.2. It's not that expensive. It's pretty cheap. Actually, I'm quite impressed by GPT 5.2. It's so much cheaper than what we used to have just a few months back with O 03 and O 01 to do this type of work, this reasoning work. So yeah, it was only a few dollars for me to get all this done. It was like $2 or $3. So for about 1,000 examples. Okay. Yeah. So let's do this. So we'll synthetically generate the data using GPT OSS 20B, and that's with our VLLM instance. So the prompt is really big. Okay, so I've already linked it here, and I need to update that link, but the link here should go to the dataset generation script. Oh, that's just a dataset. But let me look here. So the dataset generation, the data generator, right? So this thing here is the entire prompt. And yeah, how did I build this? Well, it's just through trial and error. Basically, over time, I was just generating examples and then just added more and more to it until I was happy. So I also had an LLM kind of just correct redundancy and all that other stuff to just clean it up a bit. So this is like as far as I went with the prompt. So we'll just reuse this prompt. I'm going to copy and paste that prompt as I'm demonstrating the code. So we'll do that. We'll need that OpenAI.client instance. Now, this doesn't necessarily mean that we'll be using the OpenAI API. It's just that our VLLM server exposes an OpenAI compatible API. So then we can actually use the same type of REST API calls that we would normally perform on OpenAI, but now we can just point the client instance in code to our VLLM server by specifying the base API URL, which is our 192.168 whatever in our machine that contains our B580s. And so it's a very transparent thing. So we're going to generate, so our prompt tells the model to generate 5 examples at a time. So we'll generate 5 examples at a time using that chat completions API. And then we'll just add those examples to some running list. And it will just repeat again and again until we have the number of examples that we want. Then we'll use JSON lines to just write all the examples into a JSON lines file. Okay, so now that's going to be our first thing that we need to do is we'll just create the corresponding folder. Let's call it data processing. And in order to make this valid module, we'll need an init.py. Okay, so yay, we're coding. All right. First class is going to be the data generator.py. And in our data generator.py, we want to immediately import the things that we know that we'll need. So we'll import OpenAI. That's the first thing. We'll also import JSON because we're working with JSON. We'll also import JSON lines to be able to store and write the JSON line files to disk. And then we'll need a few other things, and we'll create these helpers later. But these are the 3 base libraries we'll need. Let's just actually now just just paste this prompt in and just forget about it for the rest of the duration of just working in this file. So the method that contains this is going to be this get prompt. It's not a method, it's a function apparently. So it's a function. So we'll just copy and paste this entire function, and I'm just going to open the raw file and just do that here. It's very long, but it stops right here. So we'll just copy and paste this thing here so that we can just focus on coding. And if you really are curious about how it works deeply, I mean, you can just go to code and read the prompt exactly. But what it basically does, and let me just provide an example of what a specific example looks like that's generated off from this script. So go into the JSON-L file. It looks like this type of JSON here. If I copy this and paste it to Sublime Text and kind of zoom in a little bit, yeah, okay. So you'll have basically a JSON line that has an invalid JSON. So this string here represents the input for the example of what a user would kind of paste in, right? They'll paste in this invalid JSON, and then this fixed JSON is a key that indicates the cleaned up and escaped and pretty version of the JSON that was just input. So this is what you want the model to learn how to generate. And I just added this fixed reason here just so that I could understand what the model did to fix the JSON. We're not going to use it for this model. We'll just have a straightforward fix this JSON, and then it'll generate the fixed JSON. So this file is large. It's like 800 something lines. So we're going to be generating that, and all this was generated using GPT OSS 20B. And with a bit of quality control, it was very effective in getting that data. Okay, so now that we have the prompt here, we're going to now finally write some code. And so the first piece of code that we want to write the code that will return us back an OpenAI client. So that's straightforward. We'll just define a function called create client, and that's just going to return us a new OpenAI client instance, and it'll be provided two arguments. First is going to be the base URL, so the endpoint of where our VLLM server locally is that will host GPT OSS 20B, because that's what we want our client to hit. So we'll specify that. For my local network, it's sitting on 192.168.1.36 on port 8000 v1. So that's usually the standard I guess resource for OpenAI compatible REST servers. And then for API key, since we're not interacting with like a cloud service like OpenAI, we don't have an API key, so we just specify none just for practice. And so that's our first function to get the OpenAI client. And while we're doing that, let's start up our server. So if I brought up a new window here and I go to the models, there should have been a script to allow us to run GPT OSS 20B with port 8000. And this is the same script we wrote last time for when we had set up our B580 system. So now after this, once this VLLM instance starts up, we'll have access to GPT OSS 20B to begin generating our data. So now let's write, so how is this going to work, right? Like we're going to, so how is this going to work? So we're going to have a generate function that can be called with the client, right? And then also an attempt, which is initially 0. Now this is going to be an OpenAI .client instance. So that's what we need to tap into our VLLM server. But what is this for? Well, we need an attempt because LLMs are flaky, especially smaller LLMs. What could happen with this generate is what do we want as an output? We want our example, right? It could be the case that when we try to generate something with GPT OSS 20B, it may not even generate us valid payload. And so that can throw an exception when we want to serialize it to our example structure. And so when that happens, we'll just basically have a try except block where we can recursively call generate again with this attempt number incremented up to a certain number of attempts, and then we can just say, okay, you know what, we're not going to be able to generate this example, we'll just quit. But if it can generate the proper example within, like, let's say 3 retries, then that last result that was generated is what is going to be the example that we will use. And if it doesn't make sense right now, just, when we code it, it might later. But I just want to give you like a preview of how we're going to write this function. And also, this entire thing, right? This entire generate function is just generating one single, not one single example, batch of 5 examples, right? 5 examples. So 5 examples at a time. So it'll return back us an array of specific examples. Okay. So 5 at a time only. Why not the entire data set? Well, that's actually going to happen in a loop. And the reason why we want to do that is because we want to do this in, I guess we call it multi-threaded, or I spelled that wrong. We want to generate, so we want to call generate in multi-threaded way. So we're going to spawn 2 threads at a time to make requests to generate 5 examples, meaning that we'll have workers that will just like make requests asynchronously using futures, right? Future objects. And then when we get all the results back, we can actually tap into the futures result and get the correct batches. So we'll do that multi-threaded so that we're not stuck in just like waiting for the first 5 batches, and then we'll make the next request. We'll fire off 2 of them, and then we'll just get what we need back, and then move on to the next batch of examples to generate, up until we generate like 1,000 examples, for example. So this makes use of future objects, and you'll see how we implement that soon. Sorry, there's a lot of ums in this video and uhs because I'm just talking on the fly. Let's now define. Oh, look, it's already started. Okay, that's great. And I can hear the fans kicking. Okay, I hope it doesn't pick up the microphone because this machine is like right next to me. Anyway, let's define the signature of a function called generate, and we'll take in the client as a first argument, with OpenAI.client as the first argument, and also an attempt initialized to 0. Okay. First thing is, in a recursive function like this generate, we want to have a base case. Like, when do we stop, especially when it comes to attempts? So if attempt equals 3, we'll have 3 retries. We'll just return an empty array or empty Python list. Otherwise, in the general case, when we want to generate 5 examples, we'll just get the user prompt, and that's going to be this really long prompt gather from get prompt here. And we'll also create our messages list, which we'll do later. And then we're going to specify the model we want to use. In this case, it's GPT OSS 20B. Okay, so maybe this will be better if it's last right here. Okay, yeah, that's better. Okay, so this messages is really going to have one message. This is the payload you want to send to the OpenAI compatible server hosted in our VLLM instance. It's just basically the user message that will trigger generation. So in this case, it's just going to be that single role user. Content will be user prompt. Okay. Now we're going to send this information over using the Chat Completions API. And if you ever used OpenAI's libraries and stuff like that before, you know that it's basically using the clients.chat.completions.create method. What you need to pass in is the model. Okay, so that's the first argument. And then you'll also need to pass in the messages list. So the list of messages, or at least in this case, what we call context, right? The context of the chat so far. And you'll also need to pass in the temperature. Now, when it comes to generating data, I like to keep it at a higher temperature so it could be creative on its generation. So I usually just start out with 1.0 and I just adjust as necessary if I like what I see or I don't like what I see. But the downside with temperature 1.0, especially with smaller models, is that you could end up in a case where you often generate bad data. Even like especially if you depend on data that needs to be deserialized into an object because it's JSON, that could fail a lot of the times. So that's why we're also having this attempt here so that we can just retry it as necessary. And now you can imagine that actually this might be slow to generate data, and it indeed is. To generate 1,000 is, for at least for the B580s, it does take a few hours, but that's okay. Like that's why it's a server. Just set it and forget it. And with the way we're going to write the code, it may not be the most efficient, but it'll flush the examples every once in a while so that you won't lose any data if the script crashes. Okay, moving on. Okay, so we'll specify max completion tokens to something quite large, in this case 8K, so that in case if it's generating something big, but we don't want it to be too big because then that affects the training, right? Like in fact, like one of the things about training is that if you start to run out of VRAM quite often, probably the best thing to do is just train on smaller examples, because that sequence length is actually the number of tokens you want to train on. I actually think that maybe 8K is too much. Maybe 2048 is actually more realistic. So let's just do 2048. And then a reasoning effort. So with the cool thing about GPT OSS 20B is that it's a reasoning model, right? And it can think and produce an answer that could be more accurate than as if it didn't think and it just kind of regurgitated or like just generated tokens without kind of checking its own work before. But the downside is that it's slower to inference, right? So depending on like how you utilize reasoning, you can actually end up with really slow generations because it's thinking a lot before it actually commits to generating the result, which is what we really want. The result is that example. In this case here with GPT OSS 20B, I found it to be a really chatty thinker. Like it thinks a lot, and sometimes like the result isn't even that great compared to if you were to put it with lower reasoning. So in this case here, I specify reasoning effort to be low if our model is GPT OSS 20B. Otherwise, we'll just specify as medium effort in case if we're using 120B or Quen or anything else that may support this reasoning effort. Okay, we also want to initialize an empty list that will contain the batch of results that we will be getting from the model here at this endpoint. And this result is going to be populated from the chat message, the response that we get from the assistant. So again, so when an LLM responds back to you, that's still text, right? So what we need to do is we need to clean up that text to be able to be parsable into JSON. So we need to have a try except block for sure because there could be errors. Right, so everything here is going to be the logic, and except is going to be where we're going to just retry. So we can just return generate with the same client, but now with attempt +1 as the next attempt to make. So let's focus now on actually putting the examples into the results so that we can return it correctly. First, we need to get the assistant message. Let me see if my indentation is correct. So yeah, first we'll need to get the assistant message, which is a response from the response object. That's going to always be in choices. The first element in choices, because we didn't specify the API to generate multiple responses, we only generate one, so it's always going to be that first element. We'll look into the message object and we'll grab the content there. So that's the text content, and that could be the JSON that the model generated. Okay. However, one thing to know is that whatever is generated, and I'll just give you an example. Model will generate something like this. Since it's a thinking model, let me be more proper. Thinking content here, and then your example JSON is here. And in fact, it could end up generating something like this, right? So your LLM could end up generating payload that looks like this, where it has thinking, and then followed by a code fence for markdown, specifying JSON, and then the real JSON itself. This will not actually serialize directly to JSON. This will break. So what we need to do is we need to strip the think tags. We need to also strip away these code fences, and then we're going to have to strip away all white space to just get this portion of the data that the LLM receives, which is stored in the system message. So for that, we need to create some utilities to clean that data up. So let's create a new folder within source called utils, and we're just going to now create some helpers. So init.py for our next module, and let's first create something to strip the thinking tag. So we want to strip this away because we don't need it. We don't need that thinking process, right? So let's create a file called strip think tags.py, and then we'll write our code in here, like this little helper functions, and then it's going to be silly. It's just gonna be a simple like find, replace, and then just kind of clean that up, and then return back the new message. So strip think tags message will be the input payload. We want to return back a string. First, the easiest is that, okay, if we actually, you know what, let's do it this way. Yeah, let's do it this way. Okay, so in certain models, like the Quen model, we don't have that beginning think tag. We only have that ending think tag, right? So we can't really check for like think. Like we can't even check for like an open think and a closing think. We have to just check a closing think. So if the case where we have a closing think tag and we don't have an opening think tag because that was part of the chat template, if it's like a Quen model, we want to just return message.split. We want to just delimit by the ending think tag, split that message, and just return the second element, right? And that's the content in this case. Otherwise, we have a proper message with oops, not sub. What I was thinking at. We have a proper message with opening and closing think tags. We can use some regex to handle that. In this case, what we're looking for is something like this. Dot star question mark. Yeah, okay. So dot star question mark, and then the closing think tag here. You want to just replace that with empty, and then message will be the input payload, and then flags re.all, and then we want to just strip all white spaces, and we'll return that. So next, what we want to do is we want to strip away these code fences. That we can handle in another helper. Let's create another Python file called cleanmessage.py. And this will actually use, and this will do two things. It'll call strip think tags, so it'll clean the think tags away from the message, and it'll also get rid of those markdown code fences. So two things. So then when we get back to here, we'll just need to call this single clean message function to get clean JSON. So from utils.strip think tags, we want to import strip think tags. Then we want to define our function called clean message. That'll take in an assistant message, and then we'll output back the cleaned version of the string. So first things first, we want to strip thing tags away. So that's system message here. And then we'll just, in case, just strip away white space. Not needed since we already did it before, but just in case. Now, we want to check to see whether or not this assistant message starts with the code fence, right? That tick, tick, tick JSON. And in this case here, if it does, we want to take that substring that falls after that code fence, right? And the way to do that, the easiest way to do that is to just move that window of where the string starts, taking a slice of it, starting from the index at which this string ends at, right? This substring ends at, and we'll just like get all the content after that. So there's just string slicing. The next thing is, well, if the assistant message ends with the triple ticks, that's 1, 2, 3. Yeah, that's the ending part, right? We want to take a slice of the string from the beginning all the way up to that triple tick. So we just do that here too. I think it's just be minus len tick, tick, tick. One extra tick. So hard to see. Okay, so going from the beginning all the way up until the index that where these tick, tick, ticks start. Okay. And then finally, just the extra cleanup, we're going to just strip away white space, and we're going to return this message as the cleaned message. From here, it's easy. We'll just do assistant message equals clean message, and we'll just import that later with assistant message. And let's import from utils.clean message import clean message. So now we have our cleaned message. Nice. Next thing is, at this point, we already have, well, we can assume that we have clean JSON. So we can attempt to load the JSON now. If it's actually valid JSON, it should load into an object cleanly. So we can name a variable called generated JSON, and we can call JSON.loadS. And so load this string into a JSON object. At this point, the JSON should be valid. Now, the model generated an array of JSON, and I can print this out to kind of just show you. So print assistant message, right? So we'll see what that looks like, and then we'll that's this string here is going to be loaded into generated JSON, which is going to be basically a JSON array, JSON list. Okay, so for every generated example in generated JSON, okay, so at this point it's been deserialized into a JSON object, so we can go through this list now. We want to see if we have a valid structure. So our prompt defined that we must include, let me just give an example here. Our prompt defined that we needed to have at least an invalid JSON and a fixed JSON. So we're going to be looking for those keys, and we also want to see whether or not this fixed JSON is even valid JSON to begin with. We don't want to use an example where the fixed JSON isn't even valid, and that's easy to check. All we need to do is just deserialize that JSON inside that payload, right? So in this case here, it can be a sub try except, and I'll just write that structure here. Okay, and if it's an except, we'll just say validation error. Should we even have an exception? We know we can't turn it to JSON, so whatever. So we want to just continue with the loop. Okay. Now here's where we actually check to see if we even have a JSON. So let's write a helper to validate that. It's very easy. It's very straightforward. So let's have another utils to validate that JSON. We'll say JSON underscore validate dot py, and let's import JSON in here. Let's create a new function called validate JSON string, and then this will take in a JSON string or maybe a JSON string, and then we're going to output bool. So whether or not it's true that this given JSON string here is actually valid JSON. And then we will have a try and accept. So it's very easy. Basically, we'll return false if there was an error trying to just deserialize the JSON. So what this is really, it's just a function that will attempt to deserialize this JSON into an object. So if there's no error, basically we just execute the next line of code. So we'll just attempt to load S, and then we'll just return true because it was able to make it past this line, right? If the JSON string is not valid, it would not make it past this line. It will throw an exception, and then we'll return false here, indicating that we actually don't have a valid JSON string in this case. So going back to this logic here, we can just simply call validate JSON string, and then we'll provide in this generated example has this fixed JSON key that we're looking for, and that will give us that string value. And so if it's not valid JSON, we will print out an error, maybe error invalid JSON in fixed JSON. Okay. And then if it's all good, or we want to continue the loop. Okay, so if it's all good, we just kind of continue, like writing the code here. Okay. Or here, sorry. We're in a loop, Okay, so let's import that validator. So utils.json validate, import validate JSON string. Okay. All right. This indentation is weird. Okay, so if we have valid JSON in this case, generated example is good. We want to, in its non-deserialized form, like the raw form, we want to create our own like example structure that will be thrown into JSON lines. So we're going to append an example into the results array. Is it called result? It's called result. Okay, result.append. Right. We're going to append this object with invalid JSON as a key, and that's just going to be the same thing as a generated examples generated example here, right here. Where is it? Right here. This generated examples invalid JSON. Okay, and then this fixed JSON here is going to be from generated example. Fixed JSON. The reason why we do it like this is because we want to just take into consideration that, you know, one day maybe we want to change the prompt where it's not called invalid JSON or fixed JSON now, but the rest of our code assumes that from our data set. So you know, when that happens, we can just change these things here, but everything else stays the same. We don't have to go through like our entire code base to try and fix the consistencies. So once we have appended everything, this loop should end, and when the loop ends, we can just return the results. Okay, and then our accept here will just run the generate again if there was an error. So that's our generate function. It's pretty small, so that's okay. So to review, we're going to try 3 times in case of errors. If not, we'll just return empty result list. Otherwise, we're going to construct a user prompt. We're going to specify that we want to use GPT OSS 20B. We're going to create a messages array. We're going to call chat completions API with all this information here. Basically, specify that model, the messages, temperature of 1, because we want to be a little bit creative. We don't want to have the model be restricted to generate like a certain like type of data. And then specify for at least 2K tokens at most, not at least, at most 2K tokens. And then reasoning effort is low because this model here, GPT OSS 20B, can be quite chatty. After that, we're going to get the results from the chat completions response. We're going to clean up that string to create proper JSON. For example, we're just going to print out what that looks like before we deserialize it into a generated JSON. This should be a batch, right? This should be about 5 examples. So we're going to go through each example. We're going to validate whether or not, as a first line of defense, whether or not this fixed JSON that the model has generated to be claimed as valid JSON really is valid JSON. And then if it isn't, then we're just going to continue the loop to just generate or add the next batch in. Otherwise, if it's really bad, we're just going to say, okay, validation error. Otherwise, we're going to add the object into the list. We're going to return that batch, and then if all fails here, we're just going to retry in general. Like, let's say like the endpoint was down for that brief moment, we can just still retry. Okay, so how do we use this? We're going to have to write our main code here. For Python, it's just checking if whatever we're running is dunder main dunder. And first things first, we want to create the client so that we can actually pass that into generate. Then we want to define this results, or we should say data set. So this is going to be what we will write to JSON-L. Eventually, we'll write all this data to JSON-L file. So this will accumulate. So we're going to keep generating data after data, batch after batch, and just add them into data sets. So when we return this result here, we want to just add all these results individually into this data set. So this will accumulate up to about 1,000 examples total, right? And then we'll flush that to disk. We'll also have something, so our loop is going to continue to generate data until a certain limit. And that limit, maybe max examples, could be defined here. Maybe that limit is 1,000, right? But for testing purposes, let's just say max examples will be 5 for now, because we want to see what that looks like. Yeah, so we need a flag to just kind of have it keep generating. So I just call it keep going. And then we will have something called consecutive failures. That's just to keep track of, like, if we keep failing, we gotta just stop at some point, because we're just gonna be at a point where it's like somehow, let's say VLLM crashes. We could end up in this state where we're just like retrying, and we're going to the next, trying to generate the next example, retrying, exhaust all retries, and then try to generate the next batch of examples, because this is an infinite loop, right? We only break off from the loop whenever we have reached the max examples. We need some protection here where, okay, we reach a certain point of consecutive failures, let's just stop generating in general. So the loop is while keep going, basically while it's true. We're going to define a futures list, and that's going to contain all the outstanding future objects that we're going to be creating as we are firing off these requests rapidly. In this case, when I say rapid, it's really only 2 at a time. We'll also want to print the number of examples that we've had so far. So number of examples, and that's just going to be the len of the data set, and that's going to be an F string here. So what we need in order to do this, like firing off 2 requests at a time thing, is something called a thread pool executor. And a thread pool executor is going to create an executor object. And this executor object is what you can use to submit these jobs to be done in parallel. So that's why I kept saying it's like kind of like a multi-threaded thing. And so we get that from the concurrent library. So from concurrent dot futures import thread pool executor. So this is what we need. How we use it is just like any other resource that could be held. We need to define it with thread pool executor. We want to specify the max workers here, and let's just specify that to be 2 workers, and it gives us back an executor object. Executor object can be used to create a future. So we can create a future object by submitting a job. So we can actually import future as a type here. Future. Okay. So now we have API that we have type hints basically. So this will turn back a future. So executor dot submit. So submit a job. The first argument is going to be the function pointer, so the name of the function you want to run during submission, and the rest is going to be a list of arguments you want to pass in. Now, the reason why I was going over the arguments like this earlier is because we need to know what arguments we want to pass in to our executor, right? So we already know that we need a client, so that's the first argument. If we go back up here, that's our client. And the next is going to be the starting attempt, which we can just specify to be 0. So executor submit is going to take all these arguments and build a function call, basically. And then it'll return us back a future, and we can just append that to our futures list so that we can just, at a later time, access all those results. This part here is just getting one batch of those 5 examples that we've asked the LLM to generate. Since this is going to happen, and what a future is that you can think of it as like a promise in JavaScript. Now, if you're familiar with promises, a future is kind of like a promise in this case. So you'll access the result through an API call that future has called dot result. So yeah, I don't know how else to explain it, but basically, let's have a variable called batch found. So in case if there is something to add into our data set, and what we're going to do is we're going to iterate through all the futures we have so far. So we're going to iterate for that single future in futures. We're going to retrieve that batch that we have created so far and that we actually have something in. We're going to access the dot result to get that batch. And then we're going to check if it's in an empty array, right? So if we have something in there, we have found a batch. And then we can add all the examples in that future result into our data set. So in this case, we can do dataset.extend because we don't want to append. Otherwise, we're going to be appending a list, and then it becomes a list of lists. We want to extend where we take all the items in our batch and add it into our data set. So that would just be called .extend with that batch here. Now, outside of this, if we don't have a batch found, what we need to do is we need to increment that consecutive failures, mean that, okay, something happened, we couldn't get results for whatever reason, then we need to just maybe print out some error or warning. Yeah, let's call it a warning, not really an error yet. Empty batch generated, and then we want to emit the consecutive failures. Okay, and let's give it 5 chances. I think that's what I specified. Okay, so 5 chances to emit failures before we just quit. So if we've reached over 5 consecutive failures, we're going to just stop this loop because we've reached too many generation failures. So let's just print an error message, maybe just, yeah, error stopping due to repeated generation failures. Okay, and then we're just going to break. Okay, else here, yeah, else we want to reset consecutive failures to 0, like restart for the next iteration we're going to try and generate. Okay, so far so good. Now, after every single batch that we generate, what we want to do is we want to at least write whatever we have in our data set into a file, so that if we somehow kill the script, we would at least have some data inside the JSON lines file. Now, this is a silly way to do it, but it's quick and easy. I just use JSON lines to just write all the JSON lines. So JSON lines.open data.jsonl will be the output file. We want to specify in write mode, and then it's as easy as j.writeAll, and then the data set that you have. And we'll do that like after a certain number, I think 5, after the batches. Now, if we have generated data set, if we have generated enough of the examples, so we go over or at least max examples, we just want to set the keep going flag to false in this case. At the end of it all, is this the right? Yeah. At the end of it all, once we're done with getting all our examples, because this loop is done, we want to do one final write to the JSON lines file. So it's the same thing. It's just repeated code. Okay. So this is our data set generation script. Yeah, basically, we're going to define how many examples we want to generate. We're going to set this to whatever we want to generate how many examples in our data set. Ideally, we're going to set this to 1,000, but for now, for demonstration purposes, 5 is reasonable. And then we're going to have a while loop here that's just going to make requests to generate batches through calling generate with the client, the OpenAI client, using the first attempt, and generate then will automatically do those retries in the background. Once we get some sort of result, we can add the items in that batch into our main data set. And if we don't have anything, we increment consecutive failures. If we have more than 5 failures, we want to just stop doing what we're doing. Then periodically, we want to just kind of flush that data into this data.jsonl file. And then when we're done, once we've reached the max examples generated, we'll just do one final flush. Yeah, it's not the best way to code it, but it's simple. Okay. So yeah, let's try this out. Maybe there might be errors because I'm just coding this on the fly. So if we go to the source folder and then into the data processing folder. Wait, did we? Oh, I created it in the wrong folder. Okay, move it. Put in the egg info. This is very distracting. Okay, great. Didn't realize that. Okay, data processing. We will have the data generator. And we want to generate 5 examples, and we'll print out what the LLM generates somewhere in here. Yeah, we'll print out what the LLM generates. But at the same time, if we let it run until it generates 5 examples, we will have this data.jsonl generated in our file system too, so we can also check that. So let's do that. And so it starts out with 0. And yeah, at the moment it's just generating, and it does take some time because it is a hard task to do. You have to kind of match up, like the outputs has to be consistent here with the inputs, so that does take some time. So I am just going to let this run for a bit. So here is the printout. It looks like it did generate. It did try to generate an entire batch here. Yeah, it did. Okay, so let's take a look at what it did here. So if we look at data.json now. So now you'll have the data set. Okay, so how many did we generate? We generated 5 examples. So that's good. So notice how each example here, let's just take this one here. has an invalid JSON key. Again, this would be the user input that says, "Oh, fix this JSON," and then they'll pass in this type of JSON, and then this fixed JSON is going to be what you want to train the AI to generate given this type of input, so it can repeatedly, given these types of examples, start to pattern match. You can tell that this is formatted correctly because of all these new line characters and the spaces and all these quotes and things like that. So you want to take this string here and then kind of deserialize it to proper JSON, and then train on that. So so we're gonna do like 1,000 of these, right? We're gonna do 1,000 of these, and what ends up happening is that we're going to have to filter away the bad data using a separate script called dataset eval. So it's gonna be a while, but I already have things pre-generated. So let's just pretend, right? So in this case, we have 5 examples. So we want to next now evaluate those examples. See, we just want to take out, first of all duplicates here. Like maybe this example could be duplicated of this example, so we want to just filter that away. And then we also want to see whether or not this fixed JSON is actually a fixed JSON of the invalid JSON. So we need to create a script for that. So going back to here, dataset evaluation. So in this case, we need to use a different model to evaluate the dataset that we've generated from GPT-OSS 20B. I use GPT 5.2 to do this, but you can even spin up your own instance of Llama CPP and maybe run Qwen 330B to evaluate the dataset. It's similar in size as GPT-OSS 20B. I don't know which one's smarter. I'm assuming Qwen 330B is smarter since it has more parameters, but I think it has fewer active parameters. I'm not sure. Maybe the same. But anyway, should be able to run. The reason why I specified Llama CPP here is because I still haven't figured out how to CPU offload in VLLM with the Intel GPUs yet. Okay, so again, the rule of thumb is that it doesn't matter how you do this, as long as you don't use the same model to evaluate the data that was generated, because that would be like grading our own test in this case, and there's no point to that. Okay, so now this time we are not generating any data. We are going to evaluate. We're going to filter for good, high quality data to use for training. So we're going to create a script to automate that process. We're going to do something called LLM as a judge. What we're going to do is we're going to, again, create an OpenAI client. This instance will be the same instance that we'll be using to hit a specific endpoint. In this case, I am going to use OpenAI to do that. And then given a prompt that defines how to evaluate an example, we're going to get a single response message containing the evaluation results, basically with 2 properties in that JSON, the quality and the reasoning behind the quality decision. And then we only want to add the high quality examples because this quality key is going to determine whether or not the example is a high quality or low quality. We only want to keep the high quality of the examples, and then we want to throw away the low quality ones. Then we will save the high quality examples, and then based off of how much we have, we want to just regenerate more data, and then eventually just bring that in and concatenate into a bigger data set. So that's going to be the plan. We're going to create a dataset eval script for this. Now the prompt again is big, so I'm going to just copy and paste again. But let's just create the script first. So before I do that, actually, I will generate something more substantial. I will generate, in this case, 20, maybe 30 examples. Okay, and then come back and we'll have a bigger data set, and then we'll commit what we have, and then we'll get started writing the data set evals script. Okay, so we were able to generate 30 examples, actually a little bit over, because there were some invalid ones that were generated in the batch, so that caused the loop to continue on to keep generating additional examples until we at least exceeded 30. So this will be enough for us to demonstrate the dataset quality evaluation. We might end up with only like maybe 20 quality examples, but we'll just reuse the pre-generated data sets when we really do train. This is just to demonstrate some of the data processing pipeline. So yeah, so I'm going to create a new file called dataset eval. So we just want to evaluate the quality of the data set. In this case, we'll be importing some of the standard things that we've been importing for the other script. So it'll be import OpenAI. So we need that to make a connection to OpenAI. We'll also need to import OS because we're going to store our API key for OpenAI as an environment variable. We need to import JSON because JSON. We need to import JSON lines so that we can open up the dataset JSON-L file, filter the data, and then write to a new JSON-L file. And then our handy clean message, helper, so that we can at least clean up the judge's response into JSON, so we can extract whether or not the example that is given is high quality or low quality. We'll also now create our create client function, and that's going to give us back an OpenAI client. And just like the other one, it's going to just return back an OpenAI client instance. It's a little different this time. Instead of hitting something local, we're going to leverage os.environ.get to get an environment variable. We're going to call this OpenAI base URL, and that's going to tap into an environment variable that has the URL to hit for the OpenAI API. Same thing for API key. Since that's very private, we don't want that in code. We'll just define it as environment variable. OpenAI API key is usually the standard way of defining that. So we'll have our client created here. That will return us an instance that can tap into OpenAI. Next thing is we want to create the eval example function that will allow us to pass an example to the LLM as a judge. So you're given an example in this case, and this example has the the invalid JSON. And you also have the fixed JSON. So this payload is what you're going to be passing in to, in this case, GPT 5.2. Okay. What's GPT 5.2 is going to do is it's going to tie the eval criteria through a prompt. So like how to evaluate, right? So that's a prompt plus the example that you give, and it's going to give us back a JSON payload that will tell us the result, whether or not it's a high or low quality, and the reasoning behind that. And we're not really going to use the reasoning at all. We just want to see if we're watching logs why a certain example didn't meet the bar, right, of high. So we want the judge to give us back this. So this here will be our judge, the evaluator. So we're going to feed in every single example in the loop to this LLM here. Given this prompt that we're going to be using, plus this example here, we're going to try and get it to respond with a JSON structure that tells us whether or not this example meets the quality bar of it being something that can be used in training. And again, what a good example is let me just zoom out just a little bit. Okay, what a good example is if the ground truth is actually a valid JSON object, if it's deserialized, and if the keys and values are technically correct or the same as invalid. The only exception here is if the invalid JSON needs escape characters injected to represent the data in a correct way. So that's the flow of the evaluation. Okay, so eval example is a function that we will define, and we'll take in an example, and that's just a dictionary of the invalid fixed JSON keys. We'll take in the OpenAI client, and then we'll have a retry mechanism just like before. This one's a little easier. If attempt is going to be 3, we'll just print couldn't evaluate example for this current example here. We'll have it as an F string, and then we'll return, in this case, a fake placeholder result, and we'll just say low. It's a low quality result, given that the LLM as a judge had a hard time even trying to evaluate the examples. Therefore, it's not very good. So we'll just provide the reason as could not evaluate the example. Next, we'll define the prompt, and that will be a raw string. And I am going to just copy and paste. So that's a raw Python string. Going back to the repo, here data sets, not data sets. We're going to go to data processing, data set eval. And we're going to copy and paste this entire prompt here where we define the role. We're gonna read it together. So yeah, let's just copy all that here, and then we'll paste it just like that. And it automatically turned into an F string or not? It did, didn't it? Oh no. Let me figure this out. How do I? Did I copy too much? Yes, I did. Here we go. It's hard to tell, it's so small. Okay. Hold eyes. Okay. Triple quote literal detected at line 89. I am lost. Why? Oh, there we go. One more. Okay. So what is this prompt? This prompt first defines this LLM to be a dataset evaluator. You tell it what we're doing. So we are fine-tuning a small language model to be able to take the invalid JSON and produce. Oh, there we go. Produce a valid version of the JSON. So this includes the following: fixing all keys and values to adhere to JSON spec. This includes adding quotes and fixing values in various ways, such as adding proper escape characters, and prettifying the incoming JSON payload. Okay, so that's the role. That's the job of the LLM evaluator. Now, what's the task? So basically some background. We have synthetically generated the data set. What you need to do now is to compare the invalid JSON with the fixed JSON and see whether the fixed JSON maintains the accuracy and fidelity of key value pairs. This means that keys must not be changed in their names, and values must not be changed unless it is to add proper escape sequences, or the value is a semantic substitute for null or undefined values. So we'll also give some like guidelines, like notes right here. It's like if invalid JSON contains infinity and the fixed JSON contains infinity wrapped with quotes, then it is intentional. Not any number values must be wrapped in quotes. And then we're reminding the LLM to be mindful about keys in the invalid JSON payload with leading or trailing spaces that may be intentional and should be left alone. Consecutive commas in arrays for invalid JSON should be removed in the fix, not replaced with null or undefined. Because our fixed JSON should have technically provided that in an empty slot in this case, right? So we want to only keep the data for training if you deem them to be high quality. So output, how do you want the LLM to output? And I could use structured output for this, but just to keep it more compatible with local LLMs that may not support that, we just define it here. We want to output a JSON which contains the evaluation result of the data example. If the quality is low, then please provide reasoning. If the quality is high, then state that the quality meets the standards for the reasoning. So do not include anything other than JSON representation. So it looks like this. We have two keys, result, reason, either high or low, and then 1 to 2 sentences describing why the quality is low. Otherwise, we just say meet the standards. So we just give it a few examples of what to expect. So a user message will look like this, right? We'll pass in an invalid JSON from our dataset example, and then we'll also pass in the fixed JSON. The judge is going to look at this and go, oh, okay, that looks like a good example because this is actually a fixed version of this. So we're going to say, hi, it meets the quality standards. But we also have things like this. We want to give it invalid low quality examples given an invalid and fixed JSON. In this case here, it's quite subtle. Basically, the fixed JSON changed the name of the path to John without the H. This has the H, and we say, okay, well, for this example here, that would be considered low because the original had John with the H, whereas the fixed has John without the H. So this will result in the model like emitting incorrect results if it was to be trained on this data. So that's the reason why it's a low quality result. Okay, now we need to actually use this prompt as in this case a system prompt, and then we're going to pass the user prompt with the dataset example that we passed in here in the eval example. So all of this is still the same function. So let's build a user prompt, and then let's just build the message by hand. So using an F string. Invalid JSON is going to be the example with the invalid JSON key, value pointed by the invalid JSON key. We'll have the fixed JSON, and then we're going to pass in here in this F string the fixed JSON. So that's going to be the user message, and then we're going to create that messages array, the payload. So we're going to have that system message with the prompt, that really long prompt, but we'll also have the user message, which contains the information about the current example. Okay, and then now we're going to just call the chat completions API to OpenAI. Same thing, same API that we used last time to generate data locally. So that's why it's convenient. The model that we're going to be using is GPT 5.2. Going to use some credits. Messages is going to be the messages array we just built up the hop, and then the reasoning effort is medium. I think by default, if you don't provide reasoning effort, there's going to be none for 5.2. I think it even says it here in the documentation. Does it? Probably not. Okay. Now we get back an assistant response or assistant message. Yeah, assistant message. And then that's going to be response dot choices 0 dot message dot content. and we're going to have a try and accept to properly attempt to parse out the message as JSON to get the quality result and the reasoning behind it. If it fails, let's just say couldn't evaluate the example. Retrying attempt is going to be attempt. Put that as an F string. Okay, so attempt. Oh no, sorry. Attempt plus 1 because we're going to be trying the next attempt. And then if we exhausted all retries, we would just end up returning back this placeholder result here. I specified the reasons why earlier already. Okay, so now we have this assistant message. We got to do something with it. So now we're just going to clean that up with a clean message, passing that in, and we'll get a clean message back. And then we're going to parse that, or at least deserialize that into a JSON object, because by then everything should be good to go, and then just return the result. So that's how we evaluate a single example. So now we need to write like the code to read in the JSON lines from data.jsonl, and then do that evaluation, like filter all of it out. So that's a bit longer, but it's doable. It's easy to read. So if we write our, in this case, main method here, first things first, we want to open the dataset. So JSON lines.open, it's going to be in the same directory. So the data.jsonl, we want to read, and we want to use J as the variable. So we're going to read in the dataset. We're going to convert that to a list, so that JSON lines handle will be converted into a Python list containing all the JSON lines as a list. And then I think it's good to just specify how many we get, so that we can keep track of how much we actually end up keeping. So let's just say got len a data set training examples. And then we also want to just give a status message, because what we're going to do is we're going to dedupe. We're going to dedupe this data set, and then we're going to pass it to the evaluation phase, because we don't want to evaluate on data that is duplicated. That's a waste of money. Filtering away duplicates first will be our message here. And then we're going to, how are we going to figure out duplicates? Well, we're going to define a set, and so that's a data structure set. Then we're going to have define a unique data set that we will add examples to. Deduped, add deduped examples to. And then we're going to iterate through entire data set. Okay. Now this is going to be silly. For each example, what do we want to do for each example? Well, we want to be able to add an example in some way to the set, right? And so the way to do that is just convert that example into a JSON string where the keys are sorted so that it's consistent. And then we're going to add that to the set. And if we find an example where it serializes back to that same string, we know that's a duplicate. Okay, so that's a silly way to do it. So stringify each entire example and add to set. If set has this string, then it is a dupe. So otherwise, if not in set yet, add to unique data set. Okay, and then after that, assign unique data set as the new data set. So that's how we're gonna dedupe things. So we're gonna find a set. So we're gonna say scene is going to be set. Then we're going to define a unique data set to hold all the unique examples. So unique data set, it's gonna be empty because we're gonna add to that. And then we're gonna iterate through the entire data set. So for example, in data set, what we're going to do is for each of these examples, we're going to do example hash JSON that dumps. So we're going to turn the example into a string, and let's sort the keys while we're at it. Then we're going to check to see if this example hash is whether or not it's in scene or not. So if it's not in scene, so basically the scene set, we're going to add it to the set because it's not there yet. But we also want to add that into a unique data set because that tells us that it's a brand new example we haven't seen. And we're just not going to silently do anything if it's already in the set. We'll just keep moving on. Okay, so now finally we need to reassign the unique data set to be now the data set. Now we can start working. Okay. First things first, we want to print out the status. So how many do we have after the duplication? So data set examples after the duplication will be len of data set again. Yeah, len of data set again. And then we're going to create a client, the OpenAI client. So that's going to be one of the arguments to the eval example. Then we're going to have a filtered list, which is going to contain not only the unique examples that we have already got, but we are also going to just add examples to filter that pass the evaluation. So the high quality examples will actually be in the filter, and that's actually the one that we want to write to disk at the end of it all. So iterate through examples again, but this time going through in this new deduped data set that's been reassigned. And we want to just eval the example. Eval example, we're going to pass in the example here, the client, and then 0 as the attempt. And then we're going to print the results, just because, right? Whether or not it's high quality or not. If it's low, we'll just ignore it. So the logic here is if results, bad naming, but it's okay. If that's high, it could be either high or low. Remember, we're expecting JSON that looks like this here from our judge. Okay, so if result is high, we're going to add the example append, right, to the final filtered. So it's the same example, right? But it's just that now we know for sure that is a high quality example. We'll silently just do that, and else if the result happens to be a low quality example, we want to at least alert us like, hey, this sucks. Do something about it, but I'm not going to do anything about it. I just want to see how many. So low quality alert. We'll just print out the example that's shown, and then we'll also print out new line, and we'll print out the result so that we can read the reasoning behind why GPT 5.2 thought it was a bad example. Okay, and then by then we've iterated through our data set, assuming we've evaled every single one of them. We're just going to do one at a time. I don't want to deal with all this future stuff, and it happens fast enough that I'm not that impatient for it. Once we've processed the entire set of examples in the data set, filtered will have everything we need. When we have everything we need, we just need to write that to a new JSON lines file, and let's just add it to a new file called data filtered.jsonl with write mode on, and then we're going to then just do j.writeAll with the filtered as the argument to, or as at least all the data in filtered to the JSONL file. Okay, it's good to actually know the original number versus the filtered. So original number of examples will be the unique deduped examples, and then after filtering we want to know actually how many were actually low quality in proportion to how much that was deduped. So fstring, original number of examples, is going to be len dataset, so that's going to be the deduped data set. And then we also want to know after filtering how many do we have. filtered. Okay, like this. Okay, let's review. Okay, so what do we do here? We create a helper to create an OpenAI client. So let me quickly add my OpenAI environment variables here, and then I'll come back. Okay, so I've added my information, so now we can get a proper client created. So then we have this eval example function here that's just going to evaluate one example using GPT 5.2. If we've exhausted all attempts, meaning everything, the LLM can't seem to evaluate this specific example, we'll just return a low quality result. We'll have a prompt here that defines how to evaluate our example, and then we're constructing a user message to give the necessary data for GPT 5.2 to compare. We make the chat completions request, we get back some data, we clean that up, we attempt to load that as a JSON object, and then based off of that, we're going to add the results. Based off of the resulting quality, we're going to add the example to our filtered. Okay, so that's how it works. Yeah, so this is a process to dedupe. We're just going to use a set. We're going to do something silly, just turn the example into a straight string, and then just kind of make sure we sort the keys while we're at it, so that this way we can just do a string comparison in this case in the set, add the ones that aren't in the set yet, reassign it to data set, and then just call your evals. So let's test it on our 30 example data set. So I'll run the script dataset eval.py, and we've got 33 training examples. After deduping, it's 33, so it's unique. So far, GPT 5.2 is finding these to be high quality examples. So that's good. Okay, so it found a low quality one. So it says what? Low. Invalid JSON has speaker blah, where trailing curly quote likely represents an intended closing quote, but the fixed JSON preserves it as part of the value David, changing the speaker string content. Other fields preserved correctly, but this value alteration reduces fidelity. So that's good. It's following the instructions, right? So it is finding low quality examples in this automated script. So by the end of this, all of this, it's going to be outputting another file called data filter.jsonl, and that's going to be the set of examples that we want to use for training. So that's like our golden set. And I hope we do have a usable amount still. It would not be pleasant if we only ended up with 10. After filtering, it's good. We have kept 29 of them, so that's okay. I can proceed with that. And again, all this is for just demo purposes. I do have that data set ready to go, so by the time we start training, we can use that data set instead. But when it comes to debugging data sets and evaluating, it's good to just use a smaller data set. Okay. So now we have our evaluation data sets, evaluated data sets in our system. Think of it as the good stuff, the high quality stuff that we want to keep to teach the model. So that's good now. And again, examples are just there to show, given this input here, here's what I expect you to generate as an output. AI. And so I'm going to give you a lot of these, and you're going to take a look at each one of them, and you're going to try and start to learn how to mimic them. And if you get a new thing that you've never seen that is similar to what you have been trained on before, then you're going to try and use what you know to generate what fits with this new input. That's what you're teaching the model, you're training the model to just do that task. So that's why you need examples. Going back, what is next on our list? Okay, so now we have to split. Okay, so we have to split our data set. So let's work on splitting the data that we have deduped and filtered for high quality examples. So what we're going to do is we're going to create 3 sub data sets, and I think this is like normal practice for AI, machine learning. So we're gonna have a train data set, we're gonna have an eval data set, and we're gonna have a test data set. So the train data set is normally going to be the biggest. That's going to be the examples that you're going to be showing or training the model with. And in this case, this blog post talks about 1,000 examples, so you're going to split 900 for train data, and then you're going to use a certain percentage for the eval data and a certain percentage for the test data. So what's the difference between the eval data and the test data? So we already know that the train data is the data that you're exposing to the LLM during training, so for it to learn. The eval data set is basically the data that you use periodically to test the current model during training to see whether or not whatever results you're seeing in the training process actually translate towards the evaluation process, like the testing process, right? So if you see that the train loss is matching with your eval loss in this case, it means that your model is generalizing pretty well, because the eval data is data that your model hasn't seen yet during training. Now, as certain, in certain cases, that train data can go lower and lower for the train loss, I mean, and then that eval loss can stay the same or perhaps even increase. And what I'm trying to say is that occasionally you'll see something like this, where this is the number of iterations, and this is this is a loss basically. So you'll have your training loss kind of just go down over time, right, with your data set, but then you'll have your eval loss also maybe start out up here and then go down, but then all of a sudden climb up, right? Actually, that's not realistic. It's usually more like this, right? When this happens at this point right here, this usually means that you're gonna overfit, because your training loss right here is lower than your eval loss, but then your eval loss continues to grow compared to your training loss, where it kind of starts to get lower and lower, which means that your model during training is beginning to memorize your training data set. So this is not what you want. But I'm just saying this right now so that we can all look out for that. But that's what your eval data does. It allows you to kind of monitor whether or not your model is generalizing well on a subset of your data by running inference on it and computing the loss, so that you kind of want to keep a certain gap between the two. If the gap grows significantly, then you know that your model is starting to memorize the training data here. Okay, but then what is test data? Well, test data, you can imagine that as a way to benchmark your model. It's a subset of your data where it's not used for training or evaluation during the training process, but after the fact, this data that you have never ever seen before. It's data that your model has never seen before. And what does that actually mean? Because if eval data is the data that your model has never seen before, what's the difference? It's actually to protect from human bias. The thing is that when you pass in the eval data during training, when you start to adjust hyperparameters, like for example, learning rate, epochs, what else? Learning rate schedule, the lower rank or the lower alpha, you're kind of adjusting to kind of match against not only the training loss, but trying to get this eval loss lower. So then your judgment becomes very biased towards doing that, and you start to want to train against the eval data unintentionally. But if you have this test data set aside, what ends up happening is that you can't really adjust hyperparameters for your test data, right? You only want to use your test data as a benchmark on the final produced model. So in this case, you kind of you don't really have a sense of how to actually manipulate your parameters this way. So that kind of removes like a level of bias. And it's also good to use as a benchmark between, like, if you're trying to compare your model before fine-tuning versus after fine-tuning. This is like the best way I can explain it, and I think it makes sense to me when I think of it in that way, because it gives, again, I think it's a clearer signal on your training progress. Let's write that dataset splitting script. Usually the ratio is going to be, I believe, 80-20 for your train and then eval. But since we have 3 and we don't have that much, now the ratios that we're going to specify here is going to be 10% to eval and test. Okay, and then the rest of the 90 to train. So in this case here, this is 5%, this is 5%. The reason why for this ratio, and usually it's 80-20, but we're going to be using 90-10s because we just don't have enough data. So given that we only have about 29 examples, we're going to end up with what's 10% of this? 2.9, which is going to be 3. We can round up. So we're going to just end up with maybe 2 for eval, 1 for test, right? Oops. 1 for test. So not a good thing. I'm just thinking on the fly. What we probably want to do is go for more of 70-30. So if we have 29 examples, that would be 2.9 times 3, which is going to be 8.7 between eval and test. So let's just say 4 in this case. We're just testing our splitting logic. Again, we have a real data set that we're going to use. So this is for just demonstration. So let's just shoot for 70-30 just to see something. Okay. Yeah, so let's go and write that script. Okay, let's create a file, dataset split. Let's call it dataset split.py. Okay. Now we're going to have to take in our data filter.jsonl, put that into a list. We're going to then compute a certain percentage and that index corresponding to that percentage to extract that into that subset into training data, and then the rest will be for eval and test data. So that's pretty simple. All we need is the JSON lines library, and we also need the random library because we want to shuffle this data set so that let's say, for example, if we're going to take a slice of our array, it could be that the first few examples are biased towards being harder, or maybe the end could be biased towards being harder or easier or whatever. We want to avoid that if we're going to split our data. So let's shuffle that by using the random library. Anyway, let's open up the data sets. So with JSON lines open, we're going to open the filtered, so data filter.jsonl within read mode as J, and we're going to assign that as a list to a data variable, and we're going to random.shuffle, so mixing everything up in data, and then we're going to get the number of examples in data. So we're going to compute the index at which we need to split, like we need to go up to split the training data, and that's going to be 0.3 is going to be the ratio of both the eval and the test. So we want to do 0.15 each. So we're going to split the eval first. So we'll compute the eval split IDX. And that's going to be casted to be an integer, but 15% of the number of examples that we have. Then we're going to get the eval data and we're going to just extract that away. So we're just going to take a slice up into that eval split index, which corresponds to the 15% that we specified. And then we're going to update data because we've already changed it to just go from the split index all the way to the end of the current data. So then now our data is updated. So you can imagine it being something like this, where you start out, data as something like this, right? And then you find that eval is here. So then that's eval split IDX. And so you want to then make data go from here now all the way to the end. Okay. So that's what we're trying to do. So we're trying to just take a slice from here to here now because we've already allocated this part to be the eval data. Okay. So now we've updated data, and now we need to get the test data. So again, same approach. Test split IDX is going to be 15% times the number of examples. And then test data is going to be from data. So again, for test data, we want to find out the test split. So let's assume test is right here. So test split IDX. This is going to be, oops. This is horrible. My pen's going crazy again. Let's see here. Okay, let's just draw over it and hope it reads well. Okay, so this here, something's wrong with, okay, at this point, I think it's just the browser. Let me just reload. Something's wrong with the browser. Okay, there we go. So this is test data, right? So from here is the test data. So then we'll want to just update data again to be a smaller subset. And this will become train data eventually. Whatever is left over, right? So going back to here, again, same approach. We're going to stop at test split IDX here. And then we're going to create the train data, which is just basically whatever that is left over off from split IDX. Okay, so we have the eval data, we have the test data, and we have the train data. And we're going to be using the train data and the eval data in our training process. And the test data is going to be used for our benchmark script that we will write soon. Now that we have all this data, let's write it to a file. Train data JSON-L, eval data JSON-L, and test data JSON-L. So with JSON lines dot open, we're going to write to train data.jsonl in write mode as j.write all is going to be train data. Okay, same thing with JSON lines.open, eval data.jsonl in write mode as j.write all. We're going to write our eval data. And then with JSON lines.open, test data.jsonl in write mode as j.write all test data. Okay. Great. So if you run this script, you should have 3 new files created, right? Train data, eval data, test data, split off from the original data filter.jsonl. Okay. And so let's run that script right now. Python dataset split.py and no errors, and we got our JSON-L files here. So eval data should be pretty small. Wow. Okay, 4 examples. Test data is another 4 examples. And then this one should be 21. So 21 plus 4 is 25, plus 4 is 29. So that sounds about right. We split our data. Now what's next? So now let's begin to fine tune. Okay, it's time to make another commit, especially since our data set is, if it's large. So I'm going to make a commit just on the code files, and I'm going to then replace all the JSON-L files that we've created with the real files that we want to fine tune and test with. At this point, we know that our data generator, our data eval, and our data split scripts all work. So I'm going to just delete all these. That was a good practice to just test with. So we can commit every file here now. If we do git status, git status, we have the entire source folder. This should track, right? What's going on? Okay, or whatever. Git. Oh yeah, because I moved files. Git add. Git status. There we go. Okay, so let's say dataset pipeline scripts. I don't know why my server is being laggy, but we'll just leave it be. Okay, we have the dataset scripts all written. It's time to fine tune. I am going to download basically the data sets here. And then I'm going to copy them over so that we can use them for training. Okay, so let's just download them one at a time. Download. Okay, download our file there. Let's download eval data. Download. Okay, and then let's download test data, download, and then let's download train data, download. Okay, essentially let's just like upload all of these to do SSH to our data processing, and it should be quick. Yep, it's quick. They're actually not that big. I'm surprised. They're like less than a megabyte each. And especially since this data set here, this is the raw data set before splitting, is about 936 examples. Training data here is going to be 844 examples, leaving both test data and train data to have 46 examples each, I believe. Yep, 46 examples each. Okay. Yeah, you see my name in a lot of these examples because it's my prompt. I should have specified for it to use different names, but that's okay. This is just demo. It's just you can go back and correct anything you want to correct. Okay. We have our data set now, the real data set that we want to use. So now it's time to fine tune. Before we do that, it's always best to run your test data against the base model to get a sense on how well the normal model is doing. And remember chat client here. So chat client is going to be our test bed for like just seeing how well we're doing before we fine tune. Okay, and then we're also going to write a script that will automatically run inference on each of our models against our test set to calculate some sort of score. But for now, I want to just manually see how well Qwen 3 0.6b model does at just simply answering fix this JSON with broken JSON. And what does it actually output is what we want to see. And I'll just use this as test case. So let me go back to anti-gravity. Okay, so we are done with using GPT OSS 20B for the time being. So, using our cool ARC B580s again. So just to prove that we are on ARC B580s right here. These two, it doesn't even say it, but okay, whatever. We are going to run run Qwen 3 0.6b.sh is going to be our script that we want to run. It's going to load up Qwen 0.6b and with VLLM. So it should be pretty quick because it's a very, very, very small model. And once we load that up in VLLM, we can go back to the chat client and we can send the message to the server. Okay, so let's just copy this and then go back to our chat client. Let's just refresh that. Do we have anything? Okay, cool. Let's set the server settings. Instead of 2.9, we're at 3.6. And we want to tune down the temperatures because something like this is actually very deterministic. So now we our client has picked out that we have Qwen 3 0.6b available. So we'll just post, or not post, we'll send this message to try to have it fix the JSON. And so it does okay done this way, but you see that's kind of slow. It's like 3 seconds and it generated 229 tokens. Why? Because it's thinking. And a requirement that we want is that we want this to perform well, especially on lower end devices. And already lower end devices are going to be slower, and so we want to avoid thinking if possible. So let's try sending it with no think and then with the same message, and that's much faster at 174 tokens per second. So for the base model here, let's just always put in the no think here so that we get the fastest token generation possible. In this case, with our ARC B580s, 174.4 tokens per second is what we're getting out of the cards from. But it does more or less fix the JSON, right? But let's try a harder example. So let's try this one. This one is unique in that we have some new line characters it has to take into consideration. So let's do that. Okay. I forgot the no thing again. Let's do it again. Okay, paste. Okay, so there we go. Okay, so yeah, this one did not, so the Qwen did not get this case correct. There's supposed to be 1 new line, 2 new lines characters inside this value here, but it did quote the B. That's fine, but not what I want, because as the payload grows, it's not going to be able to correct it. Yeah, it's not be able to fix, and it becomes very unreliable, right? So that's what we're dealing with here, and I think I specified that temperature should be as low as possible, which we already have done. And then yeah, so this is just basically, I need to add the GitHub link, but this is basically how we are going to eval our model, right? We're going to create an evaluation script that will just do this with our test data set repeatedly to calculate some sort of score. Now, our requirement here is that, and this is the approach here. So we're gonna load the test examples, so the test data set, to a Python list in our script. And then for each of these examples, we're gonna perform inference on our target model. In this case, it's going to be our base unfine-tuned Qwen 3 0.6b model first. And then given the answer from whatever Qwen 3 0.6b gives us from the inference, right? We're going to compare with the ground truth. We're not going to care about formatting and spacing on this one. We just want to care about raw, like, key values accuracy, right? The ground truth with whatever the model produces. And we're going to normalize it with the spacing by first reconverting it all back to an object and then converting it back to string and indenting by 2 spaces so that spacing is like not even considered. So we give a +1 point if the model's answer matches the ground truth. And then we +0, meaning don't give any points if the model's answer does not match the ground truth. And basically we take that percentage, the ratio, to determine the score. Okay? So our test set has 46 examples. So we're going to write a script that will constantly feed that data in to just calculate the score ultimately, like how accurate the model can fix JSON. Okay, in this case now, we're going to have to create another folder, and this is going to be the folder where we have our model stuff, and we'll just call it JSON_fixer. And let's initialize it with an init.py. and we're going to create another file called model_eval.py. So this is our evaluation script. This is where we're going to load up the test data, and then we're going to just repeatedly, for every example, perform inference on our model. So we're going to need to import JSON. We'll also need to import the OpenAI client so that we can make a chat completion request to our VLM server hosting Qwen 3 0.6b. So from OpenAI dot chat, was it types? No, dot, sorry. So it's from import OpenAI. And then we are also going to import JSON lines because we need that. And then we also need to always clean our message. So from utils.cleanMessage, import clean message. And that should be it for now. Okay. So to make things easier, let's define a variable that gives the absolute path to the test dataset file, since we're in a different directory now. So it's just gonna be home, my username, code, Intel, GPU fine tune, source, JSON fix, no, not JSON fixer, data set or data processing, and then test underscore data JSON. Okay, so that's the path to the test data that we want to load up. Base API URL is going to be our VLLM instance. So it's going to be whatever my B580 machine is going to be 36, port 8000, V1, and then API key is going to be none. And then our model is going to be Qwen 3 0.6b. Okay. Now we're going to create the client, and that is going to be a OpenAI .client data type. Okay. And we're going to we're going to create an OpenAI client instance. Sorry, I'm getting tired. And this should have imported since we're scoping it down. I'm having a brain fart. Okay, sorry. Base URL is going to be base API URL. API key is going to be our API key. So we've created our client. Now we want to load up our data set, the test data. So use JSON line open, and then we're going to specify the path to the JSON file, JSON-L file, open it up in read mode, and then we're going to just add that to a list called data. Okay, now we're going to initialize the score to be 0. Then we're going to iterate through each example within our data set. And then we are going to get that invalid JSON as an input for the user input. So example invalid JSON, because every single example in our test data set looks like this, right? So we want to get this invalid JSON. We also want to get that fixed JSON later. That's for later though, in this code. So user prompt, we want to build up a user prompt. In this case, it's tricky. So for Qwen 3 0.6b, we're going to have to prefix everything with nothink because we want to go as fast as possible. And also when we fine tune our model, we're not going to consider thinking at all. So then we want to stay consistent. And so we need to generate a user message that starts with nothink, and we say only output JSON, because our base model doesn't really understand to only output JSON. And then we're going to specify fix this JSON with the input F-string. That's only if the model is equals to Qwen 3 0.6b. Otherwise, most likely we're dealing with the fine-tuned model, which will understand simply fix this JSON. There we go. Okay. Okay, now we have our user prompt. Now we want to create a chat completion. And so now we just specify a response to be that result of the chat completion. And I think we can just type hint chat completion. Maybe not. Let's import that from OpenAI.types import chat completion. I don't know why it's not working. It's weird. Okay. Was it client.chat.completions.create is going to be model, is going to be the model that we specified. So it could be either Qwen 3 0.6b or Qwen 3 0.6b fine-tuned for later. We're going to pass the messages. So in this case, it'll just be a simple user message with content being the user prompt. Okay. And then, to be fair, we gotta set the temperature to pretty low, so 0.01 in this case. Okay. And then try and accept again. Now for accept, what we want to do is we just want to silently fail, but we want to just print it out, like just let us know. So assistant message is going to be the output for whatever the response content is. So we can say whatever the model produced did not match ground truth of, in this case, ground truth. Let's just set that variable later. Okay, now what is assistant message? Again, I think everyone should know this pattern by now. It's just going to be response dot choices. Why is it not? I'm like nervous because like something is wrong with my IDE now, and I'm using anti-gravity, which is like beta, I guess. So now it's like not helping me out at this point. Okay, so I am going to just restart the extension host. Something feels not quite right with my IDE. Okay, so hopefully that works. Chat completion. Yeah, so now it works. Okay, that's okay. Okay, so assistant message, and what we usually want to do is we want to clean the message. So assistant message, and then next is we want to deserialize the assistant message to be JSON. Oh, it's deserialized to be JSON.loads. So we're going to load that into an object because we want to kind of normalize the spacing, because we're going to convert it back to a string right now. So assistant message prettified. So we're not going to alter anything. We're just going to load dump in this case to force it to just be a certain format. So indent equals 2 is a trick here to format the JSON string in a way that is spaced by two tab spaces. So now we need to also specify the ground truth, and it's the same thing. So we're going to do JSON dumps on JSON loads. So we're going to loads first with the example fixed JSON, so that's a ground truth. Then we're going to dump it with indent equals 2. So now both the assistant message prettified and ground truth ideally should just be equal if the model generates the right thing. So we need to check for that. If assistant message prettified is equal to the ground truth, we need to increment the score. Otherwise, we want to print maybe f string assistant message did not match ground truth. Okay, ground truth. Maybe assistant message prettified. Yeah, there we go. So then this will allow us to debug a little bit. Okay, so now we have that. We're constantly incrementing the score, but we need to compute the final score at the end. And so let's output that too. Okay, print f string final score for test set is going to be just cast to a float 1.0 times score over the length of the data that we have here. So yeah, this is our script to run through a specific model, in this case Qwen 3 0.6b, and just compute for every single test data example whether or not the JSON that is fixed by the model is actually matching that of the ground truth. Simple. So let's run that. JSON fixer and then Python model eval. So we're gonna run chat completion, open AI types. Dot chat. Okay. Okay, so let's fix that, and now let's run through the script on our base model. Ground truth is not defined. Why? It's right here. Already it's broken though. So that's not already good. Like, it's already an exception. Oh, the assistant message, clean message, assistant message here. And I guess just get rid of this for quick. If it doesn't match, it doesn't match. Why do we need to know, right? Okay. I could have just said example fix JSON too, but okay. So now it's running the eval, and apparently there's a lot that is not matching the ground truth. And when I first ran this test on a couple days back, it was a 54% accuracy. So this one is 52. And again, LLMs are based off of probability. So we have 52%. So let's just keep that in our head. It's about 50-ish%, like get to half right? So that's our base model. We haven't fine-tuned anything yet, okay, at this point. So now we need to fine-tune, because now we know what we have to improve on. So if we don't do this process, if we actually don't benchmark our model before fine-tuning, then we could end up fine-tuning for nothing. Because what if the base model actually can do this task perfectly fine? Then we would have spent all this time, like maybe I should have done this earlier, but we would have spent all this time creating this data set, and then trying to write all these scripts to just teach the model how to do this task, only to, at the end, to realize that, oh wait, the model has always been able to perform this task. So that's why it's good to just at least test. And in one of my cases, I was 54%. This one is 52%, but I would just say, it's the same thing. Okay. All right, so let's commit first. Again, so now we have our new data set. Let's also commit that with it. Model eval, so let's just use the GUI. And then git commit, model eval, and data sets. Okay. So now we have all that committed. And you know what? Let's just get pushed to our branch. Just cuz. Okay, there we go. What's left is now training script. Okay, let's move on to creating our training script. Okay, so this part here is pretty straightforward. If you've worked with TRL before, it's more or less the same, creating an SFT trainer with the proper configuration, and then passing in your training data set and your eval data set. And actually, to tell you the truth, all of this is just basically copy and paste code. If you've written a training script before, you'll just probably need to just tweak hyperparameters and paths to like the model and the data set itself. Yeah, there's nothing really specific to Intel hardware here, mainly because we've already had installed the Torch XPU and all the other dependencies that are required for us to use our Intel hardware. So at this point, things are abstracted at a pretty high level that you wouldn't even notice that we're going to be training on Intel hardware. So I'll just step through this fairly quickly, because it's just your training script that you can just reference on any other website. But we'll just dive into the specific parameters that can make this model good. I'd say right now we'll need to just import all these things here. So we'll import our data from our JSON-L file into datasets. We'll also need to create a custom convert to conversation function, so that we can take our training examples and then turn them into conversation objects. We'll also need some LoRa helpers. We need to wrap our model around LoRa adapters. And then we need to be able to load our model and its tokenizer by using Transformers Auto Model for causal LM and Auto Tokenizer. That'll help a lot, actually. And then we'll import SFT trainer and SFT config from TRL. Okay, let's create our training script inside the JSON fixer folder. We'll just name this train.py. I'm going to just type all the imports straight up right now. First things first is from datasets, import dataset. Okay. Next one is going to be import JSON lines. Then we also need to import the LoRa helpers from PFT import get, I think it's get PFT model, and then LoRa config. Again, I think anti-gravity's Python thing died. Anyway, import torch. We also need to import, I think, auto model for causal LM. For sure this thing died. Okay, let's restart the extension host. Okay, so let's see, auto tokenizer. Okay, we'll just run with it from TRL. So the TRL library imports SFT trainer and SFT config. Now we have one more thing that we need to import. That's our own custom code. That's the convert to conversation code. But for now, let's just write that code when we need to. I'm going to also specify a training configuration. So it's going to be a dictionary that holds all the hyperparameters and all the LoRa configuration so that we can easily modify them for experimentation as needed. And then the rest of the code itself can just reference the values off from like the keys in the training configuration. So for now, I am going to just create an empty dictionary for it, and then we'll add the right parameters later. Okay, for our model that we want to import, we want to use the Unsloth Qwen3 0.6B model as our base model, and then our fine-tuned model is going to be called the Qwen 3 0.6B fine-tuned. And then we need to point to our training data JSON-L file. So that is going to be in data processing train data. So that's where all our training examples are at, all 844, because we added in the real training data now. So let's call it train datasets path, and that will be at home, my home directory, code, Intel GPU fine tune, and then it's going to be in datasets. Source. I should have probably put it somewhere better, but anyway, data processing, train underscore data.json. Same thing for the eval dataset. We need to point that, and it's important to have that eval dataset so you can track the training and eval losses. So GPU fine tune, source data processing, eval data.json now. Okay, we have the paths. Let's just open them with JSON lines and add them to a trained dataset list. So with JSON lines dot open. Okay, this is really bothering me. How do I restart? Okay, is the Python thing crashing? I am going to kill anti-gravity, restart anti-gravity, and hopefully things will be fixed. Okay, let's try it again. It's not that I can't program without IntelliSense. It's just I'd rather have a little help. Why is it not working? Run Create environment, use existing. Okay, maybe that'll load the environment. There's something wrong with this ID. Okay, let's just roll with it. Okay, so JSON lines.open. We're going to point that to our train data set path, and then that's a read as J, and we are going to assign that as a list to train data set. And at this point, our train data set is just going to look exactly like an array of these objects here, these dictionaries here. And we need to be able to convert, in this case, convert each example to a conversation. I'm just going to code it like this, conversation. And what that looks like is just the same format that we're used to, that same chat GPT like thing where it's like role, content, and then blah blah blah, and then role. In this case, we had to provide the assistant response because that's the ground truth that the model is going to be training on. So to do that, we can write a helper called convert to conversation, like I mentioned before. Let's just create a new file that will have that helper. So we're going to pass in each of these examples here and then create that conversation example. And that's actually going to be the one that gets tokenized by the model to be able to run its inference on. So let's create that file here. We'll call it convert to conversation.py. And then let's get right on to it. We need a new utility too for this one. We need to call it JSON prettify. That's basically going to make sure that our JSON is indented correctly and is represented well to the way we'd like it. I think it's enough to just load and then do what we've been doing, right? Like just load the JSON as a string, then that becomes an object, and then you dump it again with indentation of 2. I think that should be good enough. We'll see. I had something more complicated in the main repo, but that's like for follow-up projects that I may or may not get to. So let's do def prettify JSON, and let's give it the JSON string, and then that will return back a pretty string. In this case here, we'll need to import JSON, and same thing, just return JSON dot loads, and that's going to be the JSON string. But then we want to dump. Oh, this is really hard to program without the hints. Indent equals 2. Okay, so there we go. Hopefully that works. It's simple helper, right? Going back here, we can just import that JSON pretty from JSON pretty import prettify JSON. Okay, so now we're going to define a new function called convert to conversation, and that's going to take in our training example. We're going to extract the input JSON from the example from the invalid JSON key. And we are also going to extract the fixed JSON from the training example's fixed JSON key. Okay, now we need to build our messages array. Okay, just like how we do when we inference. It's going to have role user, and we need to simulate a typical message that a user is going to send to the model, and I'm going to just type fix this JSON with new line, because that's how I usually would do it. Input JSON. Okay, so that simulates a conversation that more or less, let's see, do I have it here? It looks like this, where the user will just send fix this JSON, and then the JSON that comes, the invalid JSON that comes right after it, expecting for the model to fix it. Okay, We also need to provide that ground truth that the model is going to try and predict. So then it's another F string. Let me make sure I got my quotes, the number of quotes correct. And I'll just start from this top line here. And it's going to be fenced by a code fence of markdown JSON, just to make it look nice when the model starts to respond. And let's call our prettify JSON helper with the fixed JSON string in here. Okay, that looks good. So now what we want is we want to okay, so this is like by standard, like we just want to return a dictionary with the conversations and the message as a value. So that's going to be our convert to conversation, convert to conversation, yeah. So this will be our convert to conversation helper. And so when we go back here, we want to iterate through every single one of these examples and run that convert to conversation function and store that in the resulted, like store the results into a converted train dataset list. So we can just use like some sort of list comprehension to do that. What's going on? Expected. Yeah, something is wrong. Maybe it's my syntax somewhere. No, maybe not. Let's see. Okay. Nothing wrong with it. It's just anti-gravity. Okay. So yeah, let's just create that converted train data set. And we're going to exercise list comprehension to get this done. So we're going to import from, I think, JSON fixer dot convert to conversation, import convert to conversation. And then we're going to just transform that with convert to conversation with example pass in for each example in train data set. We'll just do the same thing with the eval data set too. So provide that eval data set path. So we're going to open up the JSON-L file, and then we're going to read and then provide that as J. Eval data set is going to be list J. Then we create a converted eval data set list. Same thing, run convert to conversation on each example. And then in eval data set is what we want. Okay, there we go. So now we have both the train data set and the eval data set converted. Next step is we want to, what's the next step? The next step is we want to load the model. So auto model for causal LM from transformers will load the pre-trained NSLOT Qwen 3 0.6b model and then also load it with the B580 data type. We also need to enable gradient checkpointing so that it's compatible with LoRa. And then we need to also load the tokenizer. So you remember how LLMs work, there's like two parts to it, right? There's like the model and the weights, right? The model weights, and then there's also the tokenizer that will transform text data into tokens that the model has understanding of. And so that's what the tokenizer is for. It also has built-in handling of the model's specific chat template. I think for Qwen, we also have to provide a padding token. I'm not sure if this is truly needed, but I've gotten used to just putting that in case. So yeah, this is how you would load the model. We haven't applied any LoRa adapters yet. And remember, we're doing LoRa fine-tuning here because we just don't have enough data. And we also don't have enough memory to actually do that full fine-tuning. And actually, in general, if you really don't have a lot of data to begin with, like what we have right now with only like 844 examples, LoRa is a great way to like prevent catastrophic forgetting, or like just pretty much destroying your model. So and given that LoRa is like kind of like really truly fine-tuning, like tweaking a really small subset of parameters, I think actually the model learns a lot better that way because it's more focused. Okay, so yeah, let's just write the code to load the model. We'll have model equals auto model for causal LM. That looks right. From pre-trained, and I think that just takes in 2 arguments. It'll be the model ID, so that's the base model up here on sloth Qwen 3 0.6b, and then we'll also specify the data type, and that's going to be torch.bfloat16. Okay, and then we're going to enable input requires grads, so that allows us to enable gradient checkpointing. And then tokenizer is going to be auto tokenizer dot from pre-trained, and that will just need the model ID as argument. Then we need to set the padding token. So I think, I don't know, maybe it's not needed after all, but we'll just add it in because I don't want to deal with issues. Okay. Let's see what else. Okay. Okay, so I opened this in a real ID, and now things look better and not throwing me off. Turns out we need to install PFT, so I'll just install that real quick. Pip install PFT, and that should just come up soon. Anyway, yeah, it's actually a horrible experience to not have hints like this. So I also need to turn off this thing here. Disable globally. There we go. Disable globally. Okay, there we go. None of this autocomplete stuff. I hate it. Okay. Where were we? Okay, so now we've loaded our model and we've loaded our tokenizer. Now we need to just define a LoRa config to do LoRa fine tuning. And yes, we have PEFT now because we're able to get type hints. Yeah, I think anti-gravity still needs to work on a few things, but yeah, okay. And remember, we have our training configuration here. So defining the LoRa config is going to tap into a lot of that. So I'm just going to assume that I have those values in the training configuration, and I'll just use them as such. So when you define like a LoRa configuration, you'll need to specify the rank, the LoRa alpha, LoRa dropout, and then bias, and then the target modules, so the layers that you actually want to fine tune. So here we're going to define the rank, and that's just going to be the access from the training configuration. And we're going to create a LoRa setting here. So let's go all the way up and do that. So LoRa, and that will be an empty dictionary. And we're going to tap into the rank. We will also have a LoRa alpha, which then we can just access in training configuration again, tapping into the LoRa settings that we're going to define. And then we're going to specify the LoRa dropout. And then we're going to do the same thing here. We're going to call that setting dropout. Bias can be set to none. And then target modules is from, again, our training configuration. LoRa target modules. Okay, so this is our LoRa configuration. Let's actually populate all that up here. So we have rank, alpha, dropout, and target modules. So let's put that in here. Rank, let's just specify 0, alpha, 0, dropout, 0, and then target modules, empty array. So how do we fill this out? Okay, so for the LoRa rank and LoRa alpha, I usually start out with 32. So that's like basically the size of the matrices that you want to fine tune. So 32 is a good starting point. I think lower rank of like 8 or 16 is kind of small. We usually don't really see good results from that. I always have to end up like increasing it to 32. Alpha is basically how loud you want these LoRa weights to be applied. So loud being like how strong. Like if you let's say specify twice the rank, basically the influence of your matrices that you fine tuned with the rank of 32, for example, is scaled to be twice the amount in this case. Dropout is actually good in this case that we provide some sort of regularization because we don't have that much data to begin with. So we want to sort of corrupt the data once in a while, like 5% of it, so that the model is forced to not really memorize the data because, in the next time it sees that example, because we'll be running a lot of epics. So next time it sees that example, it could be a little different than before. Target modules. We're going to train all layers, and I think I need a reference here. Yeah, we need to train all layers. Ooh, that's a lot. How did I? There we go. So we need to train the Q, K, V attention and O attention layers, and then we also need to train the MLP layers. That's represented by gate proj, up proj, and down proj. I'm just going to copy and paste this because it's easier. I'll just kind of fix indentation later. Okay, I'll fix indentation now. Okay, so that is basically the LoRa. Oh, I don't have the Vim extension installed. That's okay, I'll make do. Okay. Okay, so that's the layers that we're going to fine tune. So now after this, we're going to wrap our model and use that wrapped model for training. So we're going to wrap it around our LoRa adapters. So model get PEFT model. That's the helper to do that. So we're going to provide the model with the LoRa configuration. So what comes out of it now is going to be our model with our LoRa stuff applied on top of it. Okay. So at this point, we also now need to go back and think about how we're going to tokenize our example layer datasets, because right now they're all represented as like a conversation, right? So we need to go through each one of those converted like converted examples and convert them again by applying the chat template on them. And so what comes out of it is something that is more native to what Qwen 3 would expect. Let's define a helper here called formatting prompts func. And this is like taken off from like one of the Unsloth notebooks. So examples will be basically the batch. So we're passing them in batch form. So that's like an array of these conversations. So conversations is going to be in the examples, conversations key. And then we're just going to tokenize them. So we're going to tap into our tokenizer again, and we're going to call apply chat template onto them. Given for one conversation, we don't want it conversation. Yeah, we don't want to tokenize, but we want to apply the chat template on it. Okay, and then we also want to not add the generation prompt, because that is actually more for inferencing, and we are not inferencing. We are going to be training. Now we're going to just iterate through the conversation. So it's for every conversation in conversations. At this point, the chat template is applied and stored in a list of called texts. We're just going to return that as a dictionary with text as the key and the data as text. Okay, so that's how we're going to I guess I kept saying tokenize. It's not tokenize. Apply the chat template on every single one of these examples. There you go. I think I flip-flop, but it's not really tokenizing, because if we were to tokenize, they would turn into numbers. But I always want to say that for some reason. It's just basically applying the chat template. So in terms of how Qwen represents a specific conversation in a chat template, it's like something like I am start, and then like there's stuff in between, and then there's like I am end. You know what? I can just show you. How can I show you? I know. Let's search. Let's take this one. Say Qwen 3 chat template example. So you want to take this type of conversation and just turn it into this. This is what Qwen 3 actually sees. That's a chat template. And then the tokenized part will just take this chat template and turn them into the numbers that it understands. So yeah, that's what I'm trying to say. Okay. Now we need to get that data set, that final training data set off from the converted trained data set that will then be a chat template applied. So then now we can use that and pass it into our trainer so then it can train. So to train data set is going to use a data set library. We're going to convert it into a data set object from list. Converted train data set is our variable that we want to access, and we want to go through every single element here and run it through the formatting prompts func, and we're going to do it in batched mode. Okay, same thing for the eval data set. It'll be data set.from list. We want to go through converted eval data set. So that's the one with our role content examples. We want to run through every single element and run the formatting prompts func on it. Okay, batch is true. So straightforward so far. Okay. Okay, next, now we need to create our trainer object, and that's going to be the SFT trainer instance. That is actually going to be the thing that we are going to train the model with. There's a lot of arguments to it. I'm going to try my best to explain every one of them. Let's create trainer, and then let's create an SFT trainer. Okay, so the first thing, the easiest one, is to pass the model to it. So that's the model we're going to train. Processing class is going to be the tokenizer. So because I shouldn't explain it, just basically processing class is a tokenizer. Train data set is going to be the train data set that we just created from up here. Eval data set is going to be the eval data set that we created up here. So you're going to specify the data set to evaluate on. And then you have the training arguments, and that's SFT config object. And this is huge. So get ready. So it's going to be, the first option we want to provide is how do you want to access your dataset text field. So we already specified that to be text here. Dataset text field is going to be text. And then we also want to specify the eval accumulation steps. So how many times you want to actually evaluate before you send off the loss. So this one is going to be accessed through the training configuration. Train. So we're going to have a new setting called train. So let's go back up and add that in as an empty dictionary. And then we'll fill that in later. Okay, so let's go back here, train. It's going to be eval accumulation steps. Let's just try to keep it straightforward. And then the next one is going to be the eval strategy. So how do you want to trigger evals? So we want to trigger every some number of steps. Okay, well, how many eval steps do you want to trigger or eval? Every 10, every 50, every 100? So let's make that part of a training configuration setting. So that'll be part of our train key, and then it'll be eval steps. Okay. Gradient accumulation steps. I'm just trying to do it by alphabetical order. So gradient accumulation steps is how many batches do you want to evaluate before you actually send it off, like to average it, send it off to calculate loss and backpropagate and all that stuff. So training configuration, train, gradient accumulation steps. Okay. And then this one is like for memory purposes, gradient checkpointing. So then for this one, with the way I understand it, and I just hard-coded true because it's kind of necessary because VRAM. So instead of like saving all the like activations, this is what I've read, activations, and then like using all that to do that back propagation, I think you're like supposed to like just recompute them dynamically as you flow through the like that graph. So that saves memory because you're not saving all of those results. You're just gonna just use some CPU and just like recompute as needed. So how do we want to do the checkpointing? And that's going to be not using reentrant. I think this is also a VRAM optimization. And then now we specify the learning rate. So that's going to be part of the training configuration, train learning rate. We also want to specify logging steps. How often do we want to show the logs during training? Train logging steps. Okay. And then learning rate scheduler. Learning rate scheduler. Scheduler type. Yep. Let's go with training configuration train. Again, we'll come back to it. So I think we called it learning rate scheduler type. Okay. Next, the max sequence length. So max length of how you like the maximum number of tokens for that example you want to train on. So this is actually, you have to be mindful because that affects VRAM. So in this case, we're going to call it max length for training configuration. And then how many epochs you want to train for. That's also going to be something that we can configure dynamically. Okay. Train num train epochs. Then we also have the optimizer, and we're just going to be using Atom W torch. And then output directory for your checkpoints. Let's actually make that configurable. The checkpoint directory? No, output directory. Okay, same thing. Just name it the same way. It's easier. Okay, so per device train batch size is what's your batch size for every GPU you have? So be careful about this number. Basically, it's per device, meaning that if you specify a batch size of 2 and you have 2 GPUs, you're actually training on batch size of 4 effectively. So we're only training on 1 GPU, and plus we don't even have enough VRAM to kind of kick it up to a respectable number. That's why we're using gradient accumulation steps to create an effective batch size of more than 1. So I'm just going to specify 1 later, but yeah, we're just gonna do batch size of 1. So per device train batch size. And then for eval, Same thing. I'm pretty sure we don't have enough VRAM, but we'll make do. Batch size per device, eval batch size. Realistically, although it's going to be configurable, we're probably just going to provide 1 as a value. Okay. Save steps. So how often do you want to save your checkpoints? So we are going to save whatever we specify. Train, save steps. And then we also have save strategy. So in what way do you want to save per epoch? Do you want to save per step? I will specify to save per steps. Okay, warm-up ratio. What is the rate of how you want to build up to your learning rate? Like you just don't want to start at your learning rate directly, because you want to be able to kind of figure out like a direction to move slowly, and then finally ramp up to your learning rate. So in this case, it's good to provide that as a configurable number. Usually it's like 3 to 5%, I think. Yeah, of the total training steps that you have. So warm-up ratio. Oops, ration. Okay, weight. I think it's called weight decay. Okay, so weight decay is just, I'm just gonna hard code that. I think it's 0.01. Let me check. Warm-up ratio, or actually right here. Yeah, weight decay is 0.01. And then save some more VRAM, prediction loss only equals true. So that should be our last one. Okay. Prediction loss only is true. So we only want to log the prediction losses, I think. Again, I don't want to type all that again. I trust that I did everything right. If not, we'll just figure it out later. So I'm just gonna copy all this, and let's just explain like the specific value. Okay. Okay, there we go. Eval accumulation steps is just 1 because I have a problem with VRAM. I know this already because I've ran this before. Eval steps is every 100 you want to run eval. Gradient accumulation steps, you want to just start to adjust weights with basically 4 examples. Learning rate is going to be 2.5 times 10 to the negative 5. Cosine scheduling, so we're going to once we ramp up to our learning rate, we're going to decay the learning rate at a cosine rate. And then logging steps, we want to just log the losses, at least a training loss every 4 steps. Maximum sequence length, we're going to train for just for 2k tokens per example max. And then number of training epochs, I think I found that 6 is actually also affected too. Let's just do 6 to save some time. Output directory for checkpoints is going to be checkpoints. We're going to just eval with batch size of 1. We're going to train with batch size of 1. So batch size of 1 per device. We only train with 1 GPU times the number of gradient accumulation steps. 1 times 4. Effective batch size will be 4. We want to save every 100 steps. And then we want to warm up with 5% of our training examples. Cool. All right, read the blog post if you need to catch up on that. Okay, so now it's just as simple as trainer.train. That's it. That's how you trigger the training. Okay, and then once you're done with training, we just want to, and I'm just going to be lazy and copy and paste. We're going to just save our model. So how this works is, extra characters. How this works is we're going to save the LoRa adapters, okay? And then we're going to merge and unload. So we're going to merge the LoRa adapters. And then that's the merged model. And then we're going to save the merged model. And we're also going to save the tokenizer. We didn't really change the tokenizer, so just straight up just saving it. Okay, now I think that's it. That allows us to just start training our model with our data set. And so I need to kill this VLLM server, and then I will run NVTop so that we can monitor. Okay, now we're going to just look at this GPU here. We're going to run python train.py to start our training. And message, okay, so now we already have errors, so that's okay. Let's just fix it. Messages. Yeah, I have a lot of typos because I couldn't tell. Like things weren't highlighted and squiggling at me on anti-gravity. So let's start again. Let's see more. Enable input require grads. Yeah, so here we go. Example of how I can't program. Okay, fixing one error at a time. Okay, good. All right, we have 1200 steps, I guess, to do, and already our loss is 12 or 2.714. We have effective batch size of 4, and it's training pretty fast, estimated about 15 minutes to train the entire model. You see VRAM is 6 out of 12 gigs, and again, this is Intel Arc B580. I don't know how to prove it actually, but let's see. I know. Let's do XPU SMI. Yeah, okay, cool. How do we do this? I don't know how to use this. XPU SMI stats dash D0. Cool. Okay, so we're using our GPU is 91 watts now, all NA, but since the frequency is quite high, it means that we're using it. I think this thing could do better. Let's see. Let's try just doing stats, and I think it should show us. There's like one that where we had to provide the component, or maybe sudo XPU SMI dash D0. Maybe that will give us more information. Let's see. Oops. Stats. Yeah, there we go. We have a lot more. Okay. So 81 watts right now. GPU is running at a cool 54C. We have used 10 gigs out of the 12 we have, which is about right here. So yeah, trading is going well. The losses are decreasing. When it's step 200, we should start to see the eval loss. So it'll run eval, and ideally, we want to see the training loss and the eval loss following each other, right? So in about 8 more steps, we're going to see that and see if whether or not that is actually tracking. So so the eval loss is 0.64, and then the training loss is about high 0.5s to low 0.6, which is a good sign. So I think the training is somewhat healthy right now, and I expect it to be, except that this time I'm only training for 6 epochs. So yeah. Now, at some point, it could be that, like, let's say, okay, so like at some point we can say that like at the beginning, and let's just have green as a training. Things are really healthy with the green line falling downwards, right? And then this is the eval. Like the eval is also like tracking with it, but at some point, the eval loss might just plateau like this, right? So technically, again, I mentioned before, there's that point where it just becomes memorization for your model, because the eval set is something that it has never seen before, right? And so if it's not getting any better at computing or inferencing on the eval data set, it means that really what you're seeing here is just like memorization, and it's just overfitting to the training data. So the point at which the delta is lowest between the eval loss and the train loss, that's usually probably the best version of your model. Now, like to fix this, to make this better, usually you'll have to add more data, or sometimes you can just adjust hyperparameters, like for example lower learning rate, or even increase learning rate at or increase, to kind of just get to a different minima and run for more epics with dropout, or increase rank, right? But I don't want to increase the rank usually, because the base model itself was quite competent, scoring like around 50 something percent on the test data set already. So like increasing rank is just going to most likely hurt the model's base ability, and so we generally want to just like add better, higher quality data before all else, to try to get the performance of the model better. But there's another thing, right? So let's just say this, like we want to get our model better for some reason. We want to go beyond whatever percentage. Our effective batch size right now is 4. Right, effective BS. So what this means is that we will evaluate on 4 examples, average them out, and then actually use that to calculate the losses and adjust the weights with that. And so when you do that, you lose a little bit of nuance in the training examples, because like let's say there's like very fine detail about like how you treat quotes, or treat not a number values, or even comments within the JSON. That nuance can actually be lost if we are averaging out through large gradient accumulation steps or large effective batch sizes. So one easy experiment to perform if we're not satisfied with our accuracy is actually to decrease this to 2. But what ends up happening is that now your updates are a bit noisier, and it's going to be like waffling or ping-ponging in terms of like the training loss, because now it's like you're computing averages on 2, and so each one of those examples has more influence on that average, so it can move the weights in like a more aggressive direction. But if your training loss actually goes down with this, you can actually capture a lot of that nuance, and you can capture a lot of that nuance and end up with a stronger model that way. But that's actually experimentation. It's not a guarantee that it will work, but something to experiment with. Okay, now at this point, we're almost 3 epics in, and the loss for the training seems to have stabilized to high 0.4s. We can just keep letting this run and just see how far we get. I don't mind if it like kind of just diverges away from eval loss a little bit. It's okay. I mean, this is just for demo. We can always add more data or whatever in our own time. But training is still healthy. Eval loss, if you take a look at the eval loss here, it's 0.55. And then our loss here seems to be close to that. So actually, if you think about it, we still have room to improve, if assuming the eval data set is still I guess helping the model learn, or sorry, the training data set is helping the model learn. Yeah, so I'll come back later and check up on this. Okay, so I realized that I was speaking and then I didn't record a lot of what I said. But basically, here is the result of the training run. If I scroll up here, I'll just say right now that we don't need 6 epics. At some point, our training loss kept decreasing, but the eval loss was the same. And because of that, I think maybe 4 epics makes more sense. So we can actually decrease the training time even more given our data set. And um, uh, achieve the same result in this case. And I also ran, so after that, I pointed the VLLM instance to the model that was fine-tuned here in JSON Fixer Qwen 3 0.6b fine-tuned, and ran the model eval script again, but this time specifying this fine-tuned model here. And so that script runs and it performs inference on all the examples, and the result that we got was 82.6%. We can just run it again just for fun. And you'll start to see that the generations are happening, and we only output bad results. We should see some coming in soon. Okay, there. So there are some that, that aren't good, and I think that'll give still about over 80%. So 84.78%. And going back to whatever we reported here, my original result had the base model at 54.35%, while the fine-tuned model had 86.97% accuracy. So that tracks well. It trends up, but it's a significant up. It's like over 30% better in terms of fixing JSON and formatting it correctly. And remember, the test data itself was never exposed to the model, so that's all novel data, and it was still able to accurately, to some extent, format and fix. Now, I also tested this with a new example where keys were not quoted, strings were not quoted. We had consecutive commas in arrays and trailing commas in the arrays. We also had content that should have had new line escape characters rather than the new line that a human would see, and generated a few times, and I will always get a consistent good result here where the keys are fixed, the strings are quoted, the gaps in the arrays are removed, consecutive commas, things like that, and even new line character now added correctly. The amazing thing is that I consistently got 100 and well, I was getting over 141 tokens per second. So I'm still getting close. It's about 140 tokens per second now, but it's incredibly fast. By the time I scroll down, it's done generating. So quite impressive result. Next, we are going to do the same thing, but we're going to fine tune on this guy. Stay tuned. So now I'm on my QB NUC. It's booted up. And to prove that, it's a Core Ultra 7 258V. We only have 8 cores available. No symmetric multi-threading. So no two threads per core kind of thing. We have about 31 gigs of RAM. Let's just say 32 with a lot available. And the unique thing about this machine is that it actually has more VRAM than the one with the B580 if you're only going to train on a single GPU. Let me just try to show you that. Okay, yeah, here we go. So NVTop is showing us almost 16 gigs of VRAM. So we have a lot of room to spare here, but I'm just going to keep the training parameters exactly the same. I've already cloned the repo, and I'm back at the branch that we were working on. So here we go. We just need to set up the virtual environment, activate it, and then install the requirements. And since we took care in the requirements.txt, except maybe we forgot to install PEF, or we forgot to put PEFT in there, we'll just install it separately. But we already have the index URL, so we should be able to just do pip install -r requirements.txt, and things should flow. So let's create a virtual environment, Python 3.12, venv.venv. Oops, sorry. Module. Specify module. There we go. And this is just a distraction. We can just show NVTop. Okay, so now we have our virtual environment activated. Time to install the requirements.txt, and that shouldn't take too long. We don't have that much though. I think the biggest thing to install is Torch XPU, but I should have it cached by now because I've done this for a few times now. And yeah, notice how it's not really downloading much at all. So I'm just gonna sit here and awkward silence. So the requirements are installed, at least the base requirements, but we also need to install PEFT because we forgot last time, and we just did that right now. So that's okay. I think it's as simple as running a training script because my paths are usually consistent. So like the data set and everything, it's all the same path on all my computers. So I'll just cd to source. Oh wait, no, I need to pip install our own module. So pip install -e period. And then I can just cd into source JSON fixer and run python train.py and just see what happens. It should just go nicely. And okay, cool. Look, we're training on an integrated GPU. Is it slow? Let's see. Let's just have it like kind of settle. It says it's gonna take about 30 minutes to train. So we're gonna fine tune a model within half an hour. And this model is actually pretty useful if you're into JSON fixing. But just think about all the other things you can do, right? With smaller language models. The fact that this iGPU also has 16 gig of VRAM, you can also just fine tune slightly bigger models too. And there are also libraries like Unsloth, for example, that save even more memory. And I think they do support XPU. So you could actually use Unsloth to even train bigger models with this amount of VRAM. And I'm sure you'll still be in this like realm of about half an hour of training. And we're training on 6 epochs. Remember I said we only needed 4. So I would say even like you would only need less than 30 minutes to train this model. And so I think that's really cool because this mini PC isn't that expensive to begin with, especially if you're trying to get started learning AI and training and you're willing to go through the setup. It is worth that little investment. And at worst, you can just install Windows 11 on it and just use it as like a gaming machine, or even like maybe hook it up to your TV and turn it into like a smart TV replacement or whatever if you find like it's a useless machine. But from what I've been experiencing so far, I think, to be honest, like the Intel GPU stack is so underrated. I think there's too much focus on like the gaming side of things, but I think Intel has done quite well. Aside from like setup process and things like that, but in terms of like the raw hardware performance, I expected this to be a lot slower, but it is actually quite fast for what I needed to do. I would have never imagined training on an integrated GPU, especially an Intel integrated GPU. So the ARC 140V is pretty underrated, and I'm tempted to try this on an ARC 140T, even though it's Alchemist. It does have a lot like more raw horsepower behind it. I think it's like 77 tops rather than 64 tops. We can just look it up, right? Yeah, Ultra 7. GPU specifications. It is a 140T, but it has 74 tops, so 10 more tops. So I wonder how much faster that really is when it comes down to it. I have already pre-trained this model already. Let's get on to testing the performance. How many tokens per second are we going to get on our fine-tuned model with this little QBNUC? So I'm going to kill the training. Just trust me, it'll train and it'll finish the same way as the other machine. It's kind of boring if you think about it. Okay, so let's go to models. Okay, now I have a lot of models here. Okay, so run Qwen 3 0.6b .sh or ft .sh port 8000. I hope I still have the model somewhere. Wait, what's going on? Oh, there we go. Missed the B. Okay, hopefully I still have the model. If not, I'll just SCP and should be good. Intel GPU fine-tune, load it. Okay, I don't have it. BRB. Unzipped the file that I've zipped and SCP'd over. Let's see if it runs again. This time it should find the files. Okay, great. It looks like it's going. Okay, so let's go back to our chat client and just change the endpoint to, I think, 29 for me, .29. And let's see how fast the inference is. So we'll just regenerate the message again. Should be fine. So let's go to settings, change to .29 here. And then we'll just regenerate the message. That is still quite fast, about 60 tokens per second. In my tests, I would get upwards of like 61 tokens per second. So if we go back to, I should have done, it does still feel really, really fast. I would say perfect for like deployment. If you're going to just like run this or run these types of models at home. Like voice assistants and so on. You just fine tune your own small models like that. What else? Okay, yeah. The GPU, the integrated GPU, is able to give us about 61 tokens per second. But what happens if we run this on CPU? Let's say like this model is really small. It's like only 600 million parameters, and it feels kind of bad to occupy all of our GPU memory with VLLM just for a model that small. It's really fast, yeah, but can we just offload that and use CPU memory and just use a CPU to process it? How fast would that actually be? So let's do a bonus inference and let's use the CPU for this. So I'm going to fire up Llama server. Let's see, it's in my Llama CPP bin, Llama server. I'm going to try and just like put all the parameters from heart. So host is going to be exposed on all the interfaces at port 8000. The model, so the path to the model is going to be Intel GPU fine-tune, source, JSON fixer, Qwen, okay? Alias is going to be Qwen 3 0.6b fine-tuned, and then context is going to be 16384, and then threads we want 6 because we're on CPU. We want to at least have 2 free threads on our 8-thread system, so we'll just use 6 threads. NGL is actually how many layers we want to offload to the GPU. In this case, 0. Okay, we don't want any layers on the GPU at all. So let's see what happens. Okay. Oh, it needs to be a GGUF. Forgot. Okay, that's fine. That's just me getting tired. Let's do this. Let's go to our Llama CPP repo. So code repos Llama CPP. Let's activate its virtual environment and just run the convert hf gguf.py out file. It's going to be Qwen 3 0.6b fine-tune.gguf. Input is going to be the Intel GPU fine-tune at source JSON fixer Qwen 0.6b fine-tuned. So we are I accidentally stuck it into the same directory here, so let's move it to where our fine-tune repo is. So that should be okay. Okay, now Let's give this input here as a gguf. Okay, there we go. That looks better. Okay, so to prove that we are not using any GPU memory, NVTop says nothing here, and we actually are listening on the server now. Okay, now we're on CPU inferencing. It should still be the same endpoint, same model name, and so on. But you'll notice that it does take a little longer to inference, but we're still inferencing at around 42 tokens per second. That's still pretty impressive for just CPU. And we're only doing on 6 threads on a mobile CPU, a Core Ultra 7 258V, that same CPU that would be in a laptop. So I'm impressed by the inferencing speed here on CPU. We were able to fine tune a model and inference. The performance we get for the ARC 140V was 61 tokens per second. On CPU, it's 41, 42 on my other run. And then on a B580, of course, discrete GPU, much faster, almost like 2x the performance, a little over 2x the performance. When it comes to training time, we can just kind of assume that for our 140V here, it's about 3 times longer, maybe just a little over 2.5 times longer compared to the training run for the B580. And I haven't figured out how to do multi-GPU training yet, but maybe that's coming soon. I've already kind of given you my thoughts and conclusion. I'm very happy with XPU. I think there's a lot of potential, and I think it's a great alternative if you can get it set up correctly to inference and train small models with. If you use the main branch of VLLM and just install the right XPU torch library, you can run modern models as long as it fits in VRAM. And you can also fine-tune models using TRL without, like, you don't have to like pull down any extra like different branches or anything like that. If you're set up correctly, it's so transparent. I like that training script that we wrote did not have any XPU related things. In fact, this video is kind of boring now that I've only just shown you inferencing and training on the Intel GPUs itself, but there was nothing different about doing it on Intel versus like on an NVIDIA. So that experience, like once you get it up, it's a very good experience. I will be using it more. I will continue to explore how to leverage mini PCs in that way. So now I kind of understand like all this marketing around like mini PCs being AI ready, right? So if you go to like Minis Forum, for example, where they sell a lot of mini PCs, okay? You have these like AI Pro, AI whatever, things that advertise AI, but then like you kind of like look at them carefully and you're like, wait a second here, like these are the integrated video, for example. This is like a Ryzen one, and I'm just like, how is this AI, right? NPU maybe, but maybe there's a lot of potential in these integrated GPUs. Maybe like they are faster than what we give them credit for, especially if they have soldered memory. They have a lot of memory bandwidth, like DDR5 8000 and so on. That can actually increase the performance for the inference and training too. So yeah, there's a lot. For here, LPDDR5 X 7500 megatransfers per second. That's fast, right? So yeah, I'm really excited to see like what's to come, especially in 2026 with laptops and mini PCs when it comes to AI, because that just makes it more accessible and affordable to others. So maybe not the RAM part, because RAM is very expensive, but just imagine, maybe have some hope that RAM will get cheaper, and I think we'll be there. I think I'm done with exploring the Intel Arc for now, unless, like I say here, Intel, If you're watching this, you can send me a Project Battle Matrix and I'll test it. I'll promise I'll bring it. I'll send it back to you. But it'll be fun. I'll make an entire video. I'll even train the biggest model I can, and I'll document all of it. I don't know. I don't even know if anybody even watches these things.